go from the current slide. Okay. All right. I think this is where we began, left off last time. Before we get going here, let's go over just a couple of things. For those who weren't here last time, we don't know if the planetarium visit is on or off. They've got us, the earliest they could take us was February 26th, if that's a Tuesday. That's right at the end of the term. So I don't know if we're going to be able to go then or not, because by then we are trying to schedule something for Channel 13 Weather Center, because that's about the time we'll be doing that. So I don't know if there's going to be time to do it. And the other thing is, I haven't talked with the guy who's there, who I've always worked with, just his assistant, who I think is a student worker or something like that. She sent me a package. She said, you're probably familiar with this since you've been here before, but I'm sending this anyway. And in that it said we owe money to go to it, and we never have before. So I want to find out if that's for special groups or if that would count for us, because he's never said anything about money before. I don't have it budgeted, so I don't know if we can afford it or not. So there's a lot of issues. We can't go anytime soon, so we're going to just hang off and see what will happen. I've been trying to call him. I've called several times a day, every day. I never can get him to answer a phone. So I think he's really busy. They said they were stacked until the 26th was the earliest they could take us. So he must be awfully busy. And if he's generating that much money, I guess he is. I don't know. We'll see. All right. That said, we are in Chapter 18. Just barely got started in it. Not too far along in it. But we'll get as far as we can for the next at least 2 hours. If we finish the chapter in the next 2 hours, then we'll have a lab for this chapter, which is a fairly short lab in class, but it's going to be a little bit more involved for you because it's also got some questions to answer out of class. Now, you can answer them in class if you want to, but it's because it's such a short lab, I got to get up 25 points worth, and so some of it's going to be answering questions at the end of the chapter. So we'll see if we get that far today. The last 30 minutes today is definitely going to be the test on Chapter 17. So that's fixed, and we'll get as far as we can in 18 before 2 hours is up, and we'll judge from there where we'll go from there. Maybe we'll just have to continue with 18 and move into 19 and then have the lab for 18 next time rather than this time. Okay. Any questions before we get going? All right. I've noticed several people have been turning in labs that you're behind. A few people probably have missed some tests. Nobody has completed all of one lab or all the tests. For instance, Lab 1, I'm still missing 1, 2, 3, 4, 5, 6, 7, 8. Now, some of these people may not be coming anymore, but I don't know for sure yet. Test 1, 1, 2, 3, 4, 5, 6, 7. Lab 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, a few have been turned in today, so I don't know. So it's like that with all of them. I've got maybe a little over half of the people have turned it in, and almost half the people have not. So please, folks, if you are behind in labs or tests, let me know. Or, get them in. The labs into me. And the test, if you are going to go to the Birmingham campus tomorrow to take a test, please tell me so I'll have it over there. I don't want you to show up over there and then say, oh, I'm going to take a test. Well, I didn't know. I didn't bring one with me. So then we either have to come back here or, it becomes really a pain. So please let me know if you are going to show up tomorrow to take a test on Birmingham campus. I'm there from 8 to 12, actually 8 to 12:30, but I've got a meeting at 12:30, so we'll go from there. All right. Any questions? All right. So we got down to Earth's internal structure. We had started talking about some of the things in it, and this is what we have discovered. And we talked about how they discovered it, what are the criteria they used to discover it. Here's what they discovered, but we haven't tied them together yet of how they use that material to do this. So that's hopefully what we'll be doing now. 3 main zones of the Earth, okay? The first of these is the crust. Now the crust is, and now to hear it talked about, it's a thin shell that covers the surface of the Earth. Now when I say thin, I mean only a few miles thick. Okay, now that sounds pretty thick to me. But when you consider the whole of the Earth, it's just a thin shell, okay? Most of what we've ever done on the Earth, the deepest mines that we've ever dug, and everything else, we've still been within the crust. Now you might say, but wait a minute, 2/3 of the Earth is covered with water. Well, underneath the water, even though that water may be very deep, the Gulf of Mexico is already a mile deep in places, so the oceans are way deeper than that. But even then, you have a crust, okay, underneath that. We'll talk about that a little bit later. That is still a thin shell under the water even. Now, after you get through the crust, then you get into the mantle. Now, I have heard about a few places they are into the mantle. I think Russia specifically did some drilling so they could get into the mantle just to, I don't know, thinking they could get marketable material out of it. I don't know. It's much, much thicker than the crust. If you think of this little brown ridge here, and it's not that even or uniform, but that's the crust. The mantle is everything outside the red, inside the brown, including this orangey color. That's still part of the mantle. It's the biggest part of the Earth, okay? And then we have the core. The core is the center part, okay? It's the core. Now, there's both an inner core and an outer core. The outer core is this red part, lighter red. The inner part is the inner core, okay? Now, let's see. We're going to talk about each one of them separately, but keep this picture in mind as we do so, okay? Let's start with the crust. It covers the entire Earth, okay? There's 2 types of crust. The crust under the ocean, that's called the oceanic crust. Clever name. It's much thicker, much thinner than the continental crust, much thinner, but it's denser, meaning the rock that makes it up is a much heavier rock. It's basaltic rock. Now, if you remember from the last chapter, the basalts are the iron, heavy in iron, so therefore it's much denser. But it's a fine-grained rock, and if you looked at the samples I had in the lab, and if we do the day's lab, you'll see them again, very, very fine crystal size, small crystal size. And the reason is it's volcanic activity that came up under the ocean, so it cooled really quickly, small crystal size, basaltic rock. Now, under the continental crust is a much thicker crust than the oceanic crust, because it doesn't have water on top of it, but it's a lighter crust, okay? It's mostly granite rock. And if you remember granite, that's low in iron, high in silica, which is lighter density, lighter color, but the interesting thing here, most granite rock was formed deep in the Earth because it has coarser texture, larger crystal size, meaning it came up from beneath. Now, just below the crust of the Earth, there is a layer, you might say, called the Mohorovicic, or something like that, discontinuity. That's the boundary in between the mantle and the crust. Now, the main thing about this is the materials change fairly dramatically. Your seismic wave velocity increases sharply as it goes, and this is bizarre for them to say it this way. increases sharply from crust to mantle. Wait a minute, folks. Seismic waves come through the mantle into the crust. So they decrease sharply going that way. There aren't many seismic waves that go the other way. Well, when you set off a nuclear explosion or something like that, yeah, that's going from the crust to the mantle. But hopefully we don't do that very often, okay? Most of the earthquakes are down in the mantle part, and so the seismic velocity waves would be going from the mantle to the crust. So they decrease sharply there, which means, what that means to me is the density of the mantle much greater than the density of the crust. Even the basaltic density, which is greater than the density of the granite continental crust. Okay? See if there's a slide that goes with that. Yeah. This shows sort of the relative, they're not really relative thickness, but what's going on there. Now, there's one thing that's really bizarre about this graph, and we'll see it later, why they drew it this way. Obviously, the person drawing this wasn't a geologist, okay? They were just a draftsman, okay? Doing a great job, but, you know, Melanie's here across to you. There you are. Does anyone else come in since I called roll? Okay. So, I'll show you in a minute what it is. So what this is showing is the oceanic crust is underneath the ocean, mostly. Now, there are some really bizarre things, and we'll see it in some of the maps showing up later. But my wife and I, it was a couple summers ago, she had professional meetings in Salt Lake City, and it just happened to be the week in between terms for me. So we traveled together and took some extra time on the front end of our conference and traveled around some in that area. We went into Montana, Idaho, and Utah, you know, just sort of going around. I guess we were a little bit in Wyoming as well. Yeah, definitely something in Wyoming. And we went through a place, I think it was Montana or Idaho, one or the other, where we ran into basaltic deposits. Now, this is way up high elevation, probably several hundred feet, if not 1,000 feet, up in elevation, and here's basalts up there. What that means is what was at one time underneath an ocean that has been lifted up over a long period of time, lifted up until quite a high elevation. And, of course, if you think about it, what is near Salt Lake City? Where does it get its name? The Salt Lake, the Great Salt Lake, is there in Utah, several states away from any ocean, okay? And yet there's a salt lake there. That's the residue from when the land got lifted and some of the water got lifted too, and it doesn't drain out. That's residue from what was underwater. And it's way up in elevation as well. So there are basalts some places other than under the ocean. And but that's what the oceanic crust is. And this is showing it's much thinner than the continental crust. Now, this may be some exaggeration. I'm sure there's a little bit here. But that's probably close to normal or average. But the basaltic rock is much denser, and that's what they're indicating. If you had this equal volumes on a scale, the basalt would be heavier because it's a denser material. It has a lot of iron in it, and it's really cool that they drew it dark because iron is usually dark. The silicates are very light. The low iron silicates. Okay, continental crust, mostly granite rock, much thicker but less dense. Okay, the mantle is the part underneath the crust. This would be the Morovicic discontinuity, that boundary between the crust and the mantle. The mantle is usually much denser, generally a different kind of rock altogether, so that discontinuity has a lot of unusual features in it. Here's the part that's wrong of this figure. If there was any bending here, it would be the oceanic crust bending under the continental crust because it's denser. Continental crust doesn't, the light material doesn't push up the heavy material. The heavy material goes under the light material. So that's the weird thing here. That should be, if there's a bend here, the bend should be going downward, not upward. But that, and you'll see that in later figures as well. Okay? Any questions on that? So we're really talking about the crust, but we've introduced the mantle and the Mohorovicic discontinuity, which is in between the mantle and the crust. Both the continental crust and the oceanic crust and the mantle. Okay? Any questions? Now let's move to the mantle. As I said, this is the bulk of the Earth. It's a thick, thick shell between the little tiny thin shell of the crust and the core in the middle. It takes up 80% of the Earth's volume. 80%. That's 4/5 of the Earth's volume is in the mantle. It accounts for only 2/3 of the Earth's mass. What does that say to you? 80% of the volume, 67% of the mass. That means it's not nearly as dense as the core. The core is really, really dense. Okay? It's composed mainly of olivine. Okay? You'll have to go back to the last chapter and refresh your mind on what olivine is. It's a ferromagnesium silicate. What does the ferro part mean? Iron, high iron content. That's why it's dense, much denser than the crust. It's one of the iron compounds that comes out of magma early on at very high temperatures. It comes out. Then you've got your others that come out later, ending with biotite. But your augite and some of the others are in between. So olivine is a ferromagnesium silicate. Still a silicate, but lots of iron in it. And it will be, so it's pretty dense. All right. Now, how do they know this? Like I said, all of our drilling, pretty much, vast majority of drilling, anything else, has only gone into the crust. How do they know this much about the mantle? It's way down there. It's really thick. It's really hot. You know, it's not a place that we have spent a lot of time. In fact, we spent no time to speak of. So how do we know that? Well, 3 data sources. The first of these we've talked about, the seismologic data. Well, wait. How does that tell you anything about the thickness of the mantle? Well, we'll get to that, okay? It's coming up. Now, number 2, to me, is bizarre, okay? The nature of meteorites? Where are meteorites coming from? Space. So how does the nature of meteorites tell you anything about the mantle? Well, it just happens to be they're made out of some of them, not all of them. Remember, we had some that were iron meteorites and some that were stony meteorites and some that were iron-stony meteorites. The iron meteorites are basically the same type stuff, olivine. Okay, well, guess what? What is that from? That's from material that didn't consolidate with the Earth and other planets and just is still flying out there. So that, since there's so much of it out there, we must have a fair amount of it in the Earth. That's probably not the best description of it for the sun. Next, materials ejected by volcanoes. Okay? Guess what? Okay. Now, we'll see this in a later chapter. Volcanoes spit forth lava, right? We know that. But what they also know is sometimes they spit forth chunks of rock, too. And that's coming from way deep. And if that's coming from the mantle, the samples of rock that are coming up from that are very much like this. So that's how we know. They're very dense materials, more olivine than the stuff we see on the surface. Okay. Now, we've hinted at how the seismologic data is going to suggest these but we're not quite there yet. So let's hold off on that for a bit. Now, the basalt correlation. The way this bullet is put together is a little strange. It's close to the silicate chemical composition of the stony meteorites. Okay? Now, to me, that doesn't make a great deal of sense because the stony meteorites are more like the continental crust. The iron meteorites would be more like the mantle. So I don't know if they just got the word wrong or they mean the stony iron meteorites. I don't know. But that's the correlation you get between the basalts and what we see coming from the meteorites. Now, basalts are your most common volcanic rock. Why would that be? Because that magma coming up is very high iron content, though it's silicates mostly to still, but because it's made it to the surface, whether the continental surface or the under the ocean surface, it's made it to the surface, and when it makes it to the surface, it cools quickly. And by cooling quickly, you have the very fine-grained texture, okay? Small crystal size, because it cools quickly. Same thing we were seeing in the last chapter. So you see these chapters really tie together pretty tightly, okay? Now, I'm sorry I didn't turn the page in time. There is an example, 18.1, at the top of the left-hand column of 462. What is the height at which the oceanic crust floats on the mantle? There's really bizarre how they take you through this. They don't really give you enough data, I don't think, to actually do that calculation. And by the way, I meant to say this too. When I talk about the Mohorovicic discontinuity, most of the time they just shorten that and call it the MOHO, okay? A lot easier to say than the other. So 18.1 and 18.2, it's rather bizarre what they're talking about here, but you can read through that and probably still get some understanding. Okay. So that's pretty much it on the mantle. Now we're about to go to the core. Okay? Now these tie together pretty tightly. The core makes up 15% of the Earth's volume. 15% of the Earth's volume. Now remember, only three big divisions here: crust, mantle, and core. How much of the Earth's volume did the mantle make up? There it is. What percentage of the Earth's volume did the mantle make up? 80%. The core, 15%. What does that leave? 5%. The crust covering the whole surface of the Earth, under the oceans and everything else, a mere 5% of the Earth's volume. And if you think of that stretched all over the Earth, that's pretty small. Okay? Fairly thin. Only miles deep. But that still sounds pretty thick to me. But what is the mass of the Earth? What percentage of mass is the core? 1/3. What was the mantle? 2/3. How much does that leave to the crust? 0. No, negligible. Okay? It is so low in density compared to the very dense core, the really dense mantle. 5% of the volume, but it's not made up of very dense material at all. It's hardly measurable compared to the other two. So not most of the mass, but the largest, the densest part is the core by a long shot. Only 50% of the volume, but 33% of the mass. So it's almost, seems like it would be about twice as dense as the mantle. Maybe not quite, but awfully close to it. Now we get to seismologic data. How in the world do we know this if you've never been there, if you can't really go that deep? How do we know this? Well, we talked about some things before, but here are the seismologic data, and here's how we use them. Remember what we said about the P waves. Now, two other names for P waves. What could the P stand for? Anyone remember? Pressure wave, because it's compressing, okay? Number two, primary wave, because it's the fastest wave, okay? That's what P stands for. Probably primary, but you can think of it as pressure wave too, compressional wave, okay? What were some key features of that? I already said one, it's the fastest. What was another one? Because it's a longitudinal wave, it travels through, always travels through solids. It also travels through liquids, and gases too, but mostly liquids. So, when there's an earthquake event somewhere up here, generally in the mantle, okay, but somewhere up here, it's measured because, here's the thing, we'll come up with this a little bit later too. In general, the world's countries don't particularly get along that well with each other. I mean, some are fairly neutral and some, really don't like each other. And there are a few that really feel close to one another. But in general, the international community does its own thing and doesn't much worry with everybody else, except in two really major scientific areas. There's probably others too, but two we'll talk about here. And the first of these is seismological. They put seismographs, and we'll talk about these in a later chapter too, in every country on the planet. They put the same kind, the same, taking the same type measurements. They have as uniform of a system as they can get, because everywhere on the planet there's these seismographs scattered all over. One of the biggest, best international agreements that ever has been formed. Everybody contributes to seismologic data because it's in everybody's interest to do so, okay? So, when there is an earthquake anywhere on the earth, let's just say up here somewhere, and this doesn't have to be the North Pole, by the way, anywhere, okay? There's a seismologic activity here. Then they're able to measure that and read that seismological data on seismographs all the way around, more than halfway around the globe. Now this is three-dimensional, so it would go around here. Three-dimensionally, way more than halfway around the globe. Halfway around would be 90 degrees, this is 103. So it's well more than that. And down here, they read those P waves as well. Remember the P waves, primary waves? They go pretty fast. They can read them down here. The bizarre thing is, wherever there's an earthquake, there is a shadow zone through here that you can't see any primary waves. None. Zero. You see them way down here, much further away. Up here, close, but none here. What could account for that? Well, here's a characteristic of waves. Waves bend, the wavefront bends, or modify. Probably the best term for it would be, refract, when they go into interfaces between two different materials. Okay? Now, have any of you ever seen a prism? Do you know what a prism is? What does it do?
It reflects the light through it and makes it look like a rainbow.
Exactly. In fact, if you've ever seen a rainbow, you've been looking at little spherical water prisms that do exactly that. Okay? And why does it do that? The white light coming in through the air hits the water or the prism, whatever it happens to be, and there it's diffracted, meaning it's bent. And in the bending, the higher energy waves get bent less than the lower energy waves. Okay? And because of that, you get the rainbow effect. You get light split into its various colored sources: red, orange, yellow, green, blue, indigo, and violet. All those colors will show up because light, which is a wave, is refracted when it goes from one interface to another, from air to water, and then from water back to air, from air to glass, and glass back to air. Any of you like diamonds? Gals especially, probably, and some of you guys do. Yeah, I care for them. They're pretty expensive. I don't want to have to buy them, but I wouldn't mind having a few. Okay? What makes diamonds so brilliant? The way they refract light. They bend the light, because diamond is a very dense carbon structure, and it bends light more than just about any of the other materials. And guess what? That's what makes diamonds so brilliant. The light gets all refracted, and the colors show up so well. That's what makes them valuable. Okay? Well, the same thing's happening with the waves here. The seismic waves, as they go through, say, the mantle, they get bent fairly uniformly, but they still are getting bent some. But when they go from the mantle to the core is much denser, and that tightens them up. Okay? And then when they exit the core, they get spread out again. But in between, they have the shadow zone. The shadow zone, and it's every earthquake you see, there'll be between 103 degrees away from it and 142 degrees away from it. Absolutely no P waves coming through, and yet there'll be before and degrees less than 103 and everything beyond 142 up to 180. They show up, they go through, but they don't here there. Now, so the scientists have modeled and tested and come up with all kinds of theories of what could do this. And the thing that comes up is, guess what? There has to be some inner material there that's much denser than the outer material. So there has to be a core, and that would define just about the limits of the core, how big it is. So that's how they get what percent of the volume, and then other things will tell them what percent of the mass. Okay? So the P wave shadow zone, that indicates that you have a core there. It gives you approximately the size of the core, area-wise. Okay? So that shadow zone tells you that. It's used to calculate the shape and the size of the core, and it's the source of data for interior makeup of the core. Okay? As in densities, and we already know it's mostly iron material there. Basically, the meteorites tell us that, what kind of iron it probably is. And so, yeah, that's how we know the core is there and about how big it is, area-wise, volume-wise. So that's how we get 15% of the Earth's volume is the core at the center. Okay. Now, I forgot to say this. Let me go back a few slides. Sorry about this. Just dawned on me. When we had this slide, I thought they were going to come up with it sooner. That's why I left it off. But let me go back to it now. The crust, of course, is solid. Of course, water is on the crust. Just a little puddle there. You know, it's not really very much. We think it's a lot, but it really isn't very much. The mantle is a solid. The outer core is a liquid. The inner core is solid again. Now, there may be lots of reasons for that, And I'll just give you a couple that I think are important. Why is the inner core a solid? The pressure on it is so great, it's forced to be a solid, okay? Just has no choice. Why is the outer core a liquid? Well, the heat has melted the rock on the inside of the mantle down to where it becomes a solid again on the inner part. The heat is so fierce from all the friction of the movement going on and the pressure above it, it's gotten so hot it melts it. So the outer core is molten, the inner core is solid. How do we know this? That's why I came back to it, because this is going to describe why. Okay. So, let's move on to the next part. We talked about the P waves, the primary waves. What were two reasons S waves are called S waves? Anybody remember? Earth to class, come in, please. Okay. Anyone remember why the S waves are called S waves? Primary was P. It was not primary. Secondary. Secondary waves. Okay. Why are they called secondary? In the race, they come in second. The primary waves get here first. The primary waves are faster. The secondary waves are slower. That's why they're secondary. The other reason they're called S is they're shear waves. And remember the jogging the hose laying on the ground? That's a shear wave. The action is up and down, but the wave travels that way, horizontal. Okay? The primary waves are pressure waves. They go in the same direction of the pressure of the displacement. The wave is the same direction. Shear waves, they go perpendicular to the displacement. Okay? Now, what happens with the S waves, though, because when you have a earthquake up here, now notice here they did jiggly kind of lines. The P waves, they did solid lines, because those are pressure waves. They're longitudinal waves. They're in the same direction of the motion. The S waves are shear waves. They're perpendicular to the motion. Okay? And guess what? You can still see these secondary waves. They get there a little slower, but they still get there up to 103 degrees. You can measure them all over the surface of the Earth at about 103 degrees from the quake. But past that, nothing. The P waves, you get more down here, just a thin shadow zone here. The S waves, nothing. So what was another characteristic of the S waves, the shear waves, the secondary waves, that wasn't true of the P waves? Or more likely, the P waves, it wasn't true of the S waves. Anyone recall? Second? Yes, liquid. Okay. Yes, the primary waves will travel through liquids. Secondary waves are the shear waves because they're perpendicular. Water doesn't have a perpendicular nature. It's only solids that will detect that and still transmit the wave. Liquids won't. So that tells you the outer part of the core has to be liquid. It has to be liquid. Otherwise, the S waves would penetrate it. They don't. And the whole thing gets shadowed here. Okay? Now, no direct S waves are ever received here from a quake over there. Now, if the quake was here, the shadow zone would be here. They just showed this for that reason. Okay. Now, okay, a larger S-wave shadow zone extends beyond the 103 from the epicenter. All the rest of the globe is shadowed from that. The core acts like a liquid, not allowing S-wave propagation. That's how we know. Now, we also know the core has two parts. The liquid outer core, the solid inner core. See, they don't say it till here, but I felt like I need to. Now, let's go back. We know why we know the outer part is liquid, because the S-wave shadow zone, just it won't let the S waves come through. But the P waves can. But if you go back to the P wave data, notice what happens here. You have a constriction here, but then it gets really constricted here, but then spans out from there. That means that somewhere in here, there has to be a different interface. That's when you go from liquid to solid. So that's what indicates that the inner core has to be solid. Okay? There's not enough math for us to be able to describe that well. We don't have enough math knowledge, but the scientists have determined that. They've done their, modeling with all different possibilities. This is what supports what we read from the data of the S waves and the P waves. This is the only way it can work that we've been able to figure out. Okay. All right. Other core evidence. Oh, did everybody get that done? Or do you need it a little bit longer? Do I need to go back some other slides? Sorry if I went too fast. I'm sorry. By Thursday afternoon, I'm so tired. Sorry if I'm yawning. This has been a fairly long week. First 5-day work week we've had in 3 weeks, okay? We had Martin Luther King Day and then a snow day. That snow was terrible, remember? Okay. All right. Everybody got it? Okay. Other core evidence. Okay? They love these iron meteorites, don't they? And this is why it's iron meteorites. I think on the earlier slide when they said stony, I thought, yeah, it's not really the stony meteorite telling you that. It's the iron meteorite. They're mostly iron or an iron-nickel alloy. Okay? Where do they come from? They came from the really explosive activity what was happening to the Earth when it was being formed. So you just figure whatever is out there probably is inside us too. So they're thought to mimic the chemical composition of the core. That to me is an educated guess. We don't know this for sure, but it sure seems to be logical. Okay? Number 2, and we mentioned these earlier, the Earth's magnetic field. Why in the world does Earth have a magnetic field? What makes a magnetic field? This is in the first half of the book, so you haven't had it. But I told you before, what makes a magnetic field? A moving charge. Moving charge creates a magnetic field. Well, how can we have moving charges inside the Earth? Well, if the whole Earth was solid and it was all spinning, there wouldn't be any moving charges, okay? But if part of that is liquid, which we know it is from the S-wave shadow zone, it's got to be liquid. If there's a liquid that's rubbing against the solid as the solid spins around it, that's knocking off electrons and creating movement. So the source is a turbulent flow, which is flow within a liquid of the liquid form. That's what creates our magnetic field. The material must conduct electricity. Guess what a pretty good conductor is? Iron. Copper is great, but there's not much copper in there. Iron and nickel. Okay? It must be able to conduct electricity, and it must basically, I think almost has to be magnetic itself. And there's only 3 elements that are magnetic. Iron, nickel, cobalt. We don't have that much cobalt, but iron and nickel, they're in the meteorites, so they probably are in our core. And that seems to fit. The meteorite and the magnetic field data together are consistent with an iron core. Okay? Now, one thing they haven't mentioned yet, I think they mentioned it earlier. our gravitational field as well. We have a really strong gravitational field because we have a lot of mass, okay? But guess what? If all the mass of the Earth were crust-like material, we wouldn't have nearly that, okay? And we know enough about the way things go through, like the bending, refraction and stuff of those waves. You have to be getting denser and denser as you go, and in order to get the total magnetic field, gravitational field of the Earth, we have to have a lot of mass in there, and that's how we know how the mass is distributed. About 1/3 in the core, 2/3 in the mantle. The crust is negligible, mass-wise. About 5% of the volume, but negligible as far as mass goes. Now, why are we doing all this on tectonic plates? That was a lot of blah, blah, blah that didn't even mention plates. Here we get into the tie to plate tectonics. This is where it's happening. Let's look at a more detailed structure of what makes up our Earth. Okay? Well, there almost has to be, but there is a thin, hot, elastic, semi-liquid layer in the upper part of the mantle. Okay? Now this was sort of the diagram we saw before. Little bitty thin crust, a huge mantle, an outer core and an inner core. Okay? This has some dimensions on it. But let's take this very top part of the mantle, the crust and the top part of the mantle, and let's look at it separately. So we're going to blow that up over here. Now, here, approximate, there's the oceans, there's the oceanic crust, here's the continental crust, much thicker. Here's the upper part of the mantle, and then you have another layer here, and then the lower part of the mantle. This layer here is called the asthenosphere. Okay? The asthenosphere. I hope I'm pronouncing it right. It's a thin, now they show it rather thick there, but it's a rather thin, hot, well, anytime you get that far into the mantle, you're approaching some heat. Elastic. Now what does that mean? If you do something to it to perturb it, it bounces back. Okay? Like, do y'all remember silly putty? You do. Wasn't that stuff you could draw and ball, throw it against the wall, and it bounces right back? Okay, yeah. That's what we mean by elastic. Very responsive. It bounces back without distortion. Okay? So it's elastic, semi-liquid, sort of liquidy-like, but still elastic layer in the upper mantle. So here's the crust, tiny little thing up here, and then the mantle's down here. The upper part is here, then the asthenosphere, and then the rest of the mantle deeper. Okay? Now, how they know it's there is distinguished by a sharp decrease in seismic wave velocity coming through the other part of the mantle. As it goes through this, the velocity decreases and then picks back up again here. It has this thing. Well, the heat would cause that, and the elasticity, maybe less so, the semi-liquid would cause that. It's harder for the seismic waves to get through that layer, and that's why you have a sharp decrease in its velocity. So we know it's there. So what? Okay, we're going to get to the so what later. Let's first define another term with what we've already said on the board. Lithosphere. Remember what I said lith means? Rocky, rock. Remember we talked about compaction and cementation of sedimentary rocks. Lithification. Couldn't think of the word. Lithification process. That's the rock forming process. What took sediments and formed them back into a rock. Lithification. Here's a lithosphere. This is a spherical shell that is rock. Okay? Lithosphere. It's the solid layer above the asthenosphere. Well, what's above the asthenosphere? It's the upper part of the mantle, which is rock, and the crust, which is rock. Much lower density rock, but still rock. You don't count the ocean there, but you count the crust. The crust and the upper part of the mantle, that's the lithosphere. Then you have the asthenosphere, this spherical shell that's inside that, which is semi-liquid, elastic, hot, thin, and then under that you have more mantle material that goes on down to you hit the outer core. So, the solid layer above the asthenosphere includes the entire crust, all the crust, the moho for chick, discontinuity, and the upper mantle, the part above the asthenosphere that's still mantle material, but not crust material. Now, so, guess what? That semi-liquid layer, what's on top of there are your plates. Now, we haven't gotten there yet, but that's what it's going to. These plates float on the asthenosphere. Remember, it's semi-liquid, so they are able to move. They're not a solid, this lithosphere is not a solid piece of rock. It's solid, for sure, but there are cracks, crevices, there's boundaries. And those boundaries float, the pieces that make up those are the boundaries for it. They float on the asthenosphere. Okay? These are made up of rigid plates floating in the upper mantle. That's what the lithosphere is. Not a solid shell, but a series of plates that are rigid, floating on the asthenosphere and moving past each other, sometimes cramming together, sometimes putting apart, and sometimes just moving past each other. That's the whole, this is the background for why we consider plate tectonics to be the current theory of how the Earth is made. Any questions? Is it making sense? Sort of, a little bit. All right, so here's the theory of plate tectonics. Individual continents shift positions on the Earth's surface. That sounds ludicrous, doesn't it? Continents are too big to move, how could they shift? Well, the thing is, there's enough indication it has happened and continues to happen. Now, it's so slow, it's really hard to measure, but they have now measured it. If you look at the Europe, Africa, North America, South America, just look at them there. Isn't it a little bizarre how it looks like this could fit right up into Africa? The theory is it did. Isn't it interesting that where Africa bulges out here, we have an indentation here? Yeah. And look at how the eastern seaboard of the North America sort of slants to the east, and the western shore boundary of Europe shifts the same way. Okay? It looks like indeed these things could have at one time been one body. And that is the theory. Okay? Now, it's not a perfect fit, but things have altered over time. There's been some twisting going on as well as just shifting. It frankly looks like to me that Greenland could fit inside the Hudson Bay almost. Not exactly, but look pretty close. I mean, a lot of things that look fairly possible there. And some of this fit together like that. It's hard to say. Another thing that's happened, why is the Mediterranean here? Well, because these two continents are drifting apart. Very slowly, very slightly. Why is this the Red Sea up here? Well, because these are spreading apart. Why is the Persian Gulf over here? Because that's a boundary that's spreading apart. So yeah, this does seem like it is feasible. Okay? So number one, patterns between the continental shapes can be fit together. The patterns can. And there was a guy, probably 150 to 200 years ago, that said, you know, I think the continents really have drifted apart, because he was just noticing this, you know. And the rest of the scientists of the day said, you are crazy. Continents can't move. You know, they're too big and bulky. And guess what? The current theory says, nope, he was the one that's right. All you other dudes were totally wrong. Or at least it seems that way. Now, the theory is all were once part of a single large landmass called Pangaea. Now, the Gea part here is from the same root of geology, geography, the study of, you know, earth solid materials, right? And pan, anyone know what a pandemic is? How about an epidemic? Second? Yes, okay. You can have just the spread of a disease, right? Like flu has been going around pretty badly over the last few months, right? And may be continuing for a while. All this moisture we're having and then changes of temperature, it's got to be great for growing bugs, okay? But anyway, so that's what a disease outbreak is. If you have a big disease outbreak, they call it epidemic, okay? If you have almost a worldwide outbreak, they call it a pandemic. So this is meaning just about everything is involved. Pangaea, we were one big geological destruction. The original concept that the guy came up with centuries ago was continental drift, and everybody laughed him out of the room. And now we say, hey, if he was still alive, he'd say, on you, buds, because guess what? I was right, you were wrong. The plate tectonics supports that original concept. He just did it based on the shapes. Now we have a lot more evidence. Okay? What is some of this evidence? Well, evidence from the Earth's magnetic field? Yeah, we have it. Now, remember this. What are igneous rocks? Second? Okay, they don't all have ferrous, but a lot of them do. They came from, they came from molten magma, molten rock, okay? No, you're in here. Cold, right? Yeah, okay. Couldn't find you. Okay, I don't know what to do. 2:30. Okay. So igneous rocks are rocks that solidified from liquid magma, right? Okay, that's what igneous rocks are. Now, Melanie said iron. Yeah, a lot of them contain iron. Iron is one of the three magnetic materials. One of the only three elements that will show magnetic characteristics. Okay? And it's predominant. Okay? Now, we know that the Earth acts like a big magnet. Right? Now, when you have molten rock, okay. Remember let's see, how much have we talked about? I'm confusing my two classes here, I think. we've talked about fields to a very little extent, magnetic fields and gravitational fields. We haven't really stressed them too much. But anywhere you have forces like that, they are surrounded by fields. So the Earth's magnetic field is all around. That's why I can go down to the physics lab, pull up a compass, it's going to point to the north, because the Earth's magnetic field is all around us here, pointing toward the north. Okay? So the field is here. It's pretty much always has been here. Okay. Now, I can't say much about this, but it says the igneous rocks record the magnetic field strength and direction of the Earth's magnetic field. Because the iron that's in the igneous rock aligns itself, especially when those fields are strong, they're just like magnets. Now we know this because the earliest magnets they discovered when they dug up rock and they found out it was magnetic. And then when they rubbed other magnetic material against that magnetic material, they made other magnets. And those magnets, if you let them float, always pointed north. Northward anyway. Okay? So we know, that's how we know the magnetic fields are there. Okay. The rock are recording the Earth's magnetic field strength. As the rock comes up as liquid and solidifies in the presence of the Earth's magnetic field, it aligns itself with that field, and it forms magnetic material itself. Now, over the years, there are these igneous rocks that came out of magma, okay, especially where the magma came to the surface and then solidified. There are some places that field is very strong. You have very strong magnets there. Other places it's very weak. That indicates the Earth's magnetic field must have been weaker there. And they have layers that are weak and strong, weak and strong. Okay. Igneous rock record that field strength and the direction. Wait a minute. I thought that magnets always pointed north. They have during man's lifetime, but we haven't been around very long, especially knowing about magnets. I think I've given this illustration before, but if not, I'm going to give it now. If this was the point at which the Earth was formed, okay, right here, and this over here is right now, okay? Earth formed right now. How long do you think man's been around? Where should I start and stop? You tell me. Is it closer to that or closer here? Tell me. Which way to walk? Huh? Where I am now? About here? Okay. Anyone else?
Man's been around since the beginning.
What's that?
Man has been around since the beginning of the Earth.
Since the beginning of the Earth. Oh, okay. Geologically, they don't find any evidence of that because even in all documents, there's a period of time before man was created, right? Is that what you're referring to? Hold up. Okay. Our best understanding from everything else, we have been around about maybe that long. Okay. The Earth has been around, according to what we know of fossils and everything else, we've been here very little. Dinosaurs were here, we think, probably before us. I don't know that man ever really saw dinosaurs. Maybe they've been dead a long time. Other things, the fossil records, and even them, you know, there's just a lot of evidence that we are fairly newcomers. So all the time we've been around, magnets are pointed north. But when they dig down in the rocks, way before that, we find that here the rocks are pointing to, magnetic fields were pointing south. Here they were north, here they were south, here they were. That there have been something like 22 reversals in the past 4.5 million years. Now remember, the creation of the Earth was about 4 billion years ago, maybe 4.5 billion, something like that. I hope they got the number right here rather than... sorry to break like this, but I just realized I haven't been turning my pages well here. At the top of page 464, there's a little blurb on seismic tomography. Does anyone ever run into the word tomography before? Have anyone ever heard of a CAT scan? Okay, that is computer-assisted tomography. Okay, that's how you can measure or put together what's inside someone's body. I, many years ago, had what they diagnosed as a heart flutter. It wasn't a, what are the more dangerous thing? I can't think what you call that. It was just a flutter. And I've had about 3 of them that I can think of. They've been about 7 to 13 years apart, so they don't happen often, but I happened to have one when I was at the doctor's office. They sent me up to cardiac. They started measuring things, and no, actually this was before then. I told the doctor about it. This was before I was there, and they did a kind of a tomography on me, and they actually then computer-assisted drew a picture of my heart and how it was operating, and it was great. There was no heart problem at all. It just was a rhythm problem. It's not an arrhythmia, it's a flutter. That was it. So anyway, seismic tomography, they're talking here about how they can study the interior of the Earth without going into the interior of the Earth, just like they drew pictures of my heart without going into my heart. Thank goodness. Okay, so anyway, that's what that is talking about. Okay. Let me see if I can find this. Yeah, they still have 4.5 million. That's what it was to make sure they didn't mean billion. So guess what? If that was 4.5 billion years ago, past 4.5 million years would be somewhere down here. I mean, there's 1,000 times difference between billions and millions. So you would be way down there. Okay? So 22 reversals over the past 4.5 million years, which is a fairly short time period. But we haven't been around 4.5 million years, but they can tell this from the fossil records, you know, best they can tell. Okay? 22 reversals over the past 4.5 million years. Okay? I cannot begin to tell you how those could happen. I can't even imagine how they could happen, but the rocks show it. Okay? They show that there have been these reversals over time. Why are we talking about Earth's magnetic field records and rocks when we're supposed to be talking about plate tectonics? Well, here's why. Oh, this is a figure illustrating it. When cooling lava solidifies in the presence of the Earth's magnetic field, it lines up the iron in there in the directions of that field. And it's been doing this from age immemorial. However, you have layers of rock that the field is one way, and then you have layers where there's not much field at all, and then layers where the field is pointing in the opposite direction, and then not much activity at all, and then going back this way. 22 reversals of the past 4.5 million years. And we haven't been around 4.5 million years. We are all in the last reversal when we are all pointing north. Later, if we're around long enough, it'll probably point south again. Now, here's the only thing I can figure is happening there. The variations must be a very slow sinusoidal activity. Very slow, okay? And sine curves is sometimes up here, sometimes down here. Everything operates according to sinusoidal. A lot of things do rhythms, okay? And it must be, when they're up here, they're pointing north. Down here, they're pointing south. In between, there was very weak field. Not very strong at all. They're not really recording much magnetic activity at all. Okay, so they have discovered this. 22 reversals of the past 4.5 million years. How they know that? They drill down into the rock, and they see the rock changing magnetic fields 22 times over 4.5 million years. Okay? All right. They're saying evidence from Earth's magnetic field, but they don't say how it applies. We'll get to that. Evidence from the ocean. All right. Let's go back to this picture right here. This is the Atlantic Ocean. This is where it looks like the continents could have drifted apart, leaving this. Well, sure enough, guess what they've discovered? Smack dab in the middle, or pretty close to it, of the Atlantic Ocean, going right up here. You see this little island here? Does anyone know what that is? It's a country. Very cold country. Well, it's really cold. You may have it in your cup there. I don't know if you do or not. Ice! And this is Iceland. Iceland is a volcanic island right up there in the middle of the Atlantic. Iceland is the only part that I know of that's above the surface of a big ridge. But you can go along, and they have done it. They've taken sonar and gone across the Atlantic, measuring depth, and sure enough, in the middle, it comes up, and then it goes down again. There's this ridge in the middle of the Atlantic Ocean. Right? And Iceland's on that, and Iceland is a volcanic island and a series of islands. Well, guess what that means? That means there has been volcanic activity all along that ridge, building the ridge. Iceland's the only part that's above the surface, but it is all along there. Okay? So that's what they mean by oceanic ridges. Okay? They coincide with submarine earthquakes and submarine volcanic activity. Now, several editions ago in this book, I'm guessing 3 or 4 editions ago, rather than sending a CD or DVD with it, they sent a package of DVDs and CDs. I wish they still sent those. They don't, okay? And one of those in the package, I can't get it to work anymore. It must have been time fixed so that after a certain while you couldn't use it anymore. But anyway, they had the most incredible video. They actually had lowered a camera down into the middle of the Atlantic Ocean and recorded an underground volcano going off. And you could see this magma, which now was lava, bubbling up and really turning the rock quickly because the waters are really cold that deep. And you could see this, and you could just, they were pulling it along. You could see it just come up and come up and come up. Most incredible video I think I've ever seen. Okay? Amazing. Okay? So that's the sub-oceanic ridges. They coincide with these submarine, meaning underneath the water, earthquakes and volcanic activity. They make a rift along the crest, and there's a large amount of heat escapes from the crest, so they've been able to measure the heat in the ocean and know that there's always pretty much activity along that ridge. So we know it's coming from volcanic activity or earthquake activity. That is called the Mid-Atlantic Ridge. It's there. They've measured it. They've filmed it. You know, they see it formation. Okay? Now we also have oceanic trenches. And this is referring back to that error I was pointing out in that drawing that we had. These are long, narrow, deep troughs with steep sides. Okay? Now, we're not going to hit these until a little bit later, but they always run parallel to the continental edges. So let me go back to this picture again. And it's not so much on the Atlantic side, but on the Pacific side, all along. You can't see North America here, but we have them. And South America, you have these trenches that right up there, they suddenly get really deep. You would think as you approach land, they would get shallower. And I was stationed when I was in the Navy the first 3 years on a ship that went out of San Francisco Bay Area, okay? And we went under the Golden Gate many a times, you know, that I was also the deck a few of those times. And when they did do soundings, you would see that and even the charts and stuff, just right outside the Golden Gate, I'm not sure if it's still within sight of land or not, but it just plummeted. Really steep. You would get these, and then it would come up again. The bottom would come closer. Not a lot closer, but some closer. There would be a trench right along the edge of the continent. Okay, and it followed that. Okay? Sorry, on the wrong slide here. So that's what we're meaning by long, narrow, deep troughs with steep sides parallel to the continental edges. Okay, they're not going to tell you why yet, but we'll get there. Just keep that in mind. We know those exist. We know the ridges exist. We know those trenches exist. Okay? Now, this is the illustration of the Mid-Atlantic Ridge, and they call it the Rift Valley. This is approximate. It's not exact. But notice how it's almost always equidistant between the continents. Almost always. Okay? Iceland just happened to be where it came to the surface. Iceland's a volcanic island. They still have active volcanoes there. And actually, I said, you know, the name is Iceland. Look how far north it is of England, Scandinavia, parts of Greenland that's even further. I mean, it's way up there, okay? Would you think the people who live there spend most of their income heating their homes? It's cold up there. Really cold. They spend almost nothing heating their homes. Why? What the Icelandic people have done, I guess their government has done, they pipe water down near the hot rock, volcanic rock, and pump it back to the surface and then run it into people's homes under the floors. They're built this way, and they heat their homes using thermal energy. Geothermal energy from the earth. They don't spend any electricity to speak of heating their homes. They don't use a lot of fuel and stuff like that heating their homes. They use the earth because there's volcanic rock. Now they've always messed up a few times because they'll drill down near the volcanoes to get more of the heat. A couple times they've hit places that actually almost created a new volcano coming up. Whoops, let's cut that one off. We don't want lava coming up here. But they have experimented with it, and they do most of the heating of their homes and businesses through geothermal, pumping water down and back up, hot water flowing up. So they're part of that Mid-Atlantic Ridge. Okay? So there's the first part. What do you think that is? That's a boundary between plates, tectonic plates. That ridge right there is. Okay. So here's the seafloor spreading hypothesis. Okay? And by the way, if the continents have been closer at one time and they're spreading apart, and that's what's creating the spread, because the magma is coming up here and pushing out, that's what pushed the continents apart. Okay, to take you back there. So, here's the hypothesis. Hot molten rock moves up from the Earth's interior, emerging along a rift, like the Mid-Atlantic rift. The outflow in both directions creates new rock. Okay? Now, remember I said they would drill down. This is how they got information about the changing magnetic field. Then sedimentary layers. Now, this isn't sedimentary rocks. This is igneous rock that settled out, okay, near the ridge, become thicker as you move to the continents. Okay, let's see if we can sort of get a picture of what they're saying here. This is not a good picture of what they're saying. Well, it is, but you got to sort of figure. They have taken samples from right near that ridge, okay, and those samples, all the indicators of those who are within the last 5 million years. Okay, 0 to 5 million years old. On either side of that, they've taken other samples. They take samples all the way across, and on both sides of that, they find evidence of 5 to 23 million years. And then on either side of that, they find 23 to 38 million years. On either side of that, 38 to 53 million years. Things are getting older the more you move away from the ridge. The rocks are older. The sea life that was caught in the rocks is older. The carbon dating is older. Everything's older. Nothing old in here, and it gets older the further you go. Finally, as you get near the continents, you're 66 to 135 million years. Okay? Now, remember 4.5 million? It's all in that part. We've seen that many changes of our, 22 changes of our magnetic field. Okay, whoa. All right. That's why I was wondering if that wasn't really 44.5 billion, but they said million. Okay. So the older fossils and rocks are near the continents and getting nearer and nearer and nearer near the rift. Meaning this is all new material coming up, pushing out, spreading the continents further apart. But notice how long this is taking. Millions, hundreds of millions of years this has been going on. Okay. Older fossils are there. All right. Now, that's the drilling evidence. The magnetic seafloor spreading evidence. Okay, we talked about the magnetic layers. Those have been alternating 22 times over the last 4.5 million years. The paleomagnetic, that's the old magnetic pattern. Paleo means old, ancient. Of magnetic strips in the ocean floor, basaltic rock. All this making sense of what we talked about before. Identical magnetic reversal patterns on both sides of the ridge. More patterns further out, fewer patterns near the surface, but they're identical on either side of the ridge. Not identical near it, or they're on opposite sides they are, but they are changing the more you go in, but the patterns match those found elsewhere, providing age determination. So they've been able to do this, test these patterns here with patterns, say, in the Pacific and other places, estimating ages and stuff like this. All of the data has come together, indicating, sure enough, there is spreading in the middle of the Atlantic. The continents were drifting apart because of that spreading. Okay, very slowly, incredibly slowly, hundreds of millions of years for them to spread the amount they've spread. Okay, I think they measure it in so many centimeters a year. Okay. That's tiny amounts, okay, in a year. Did I leave the last slide too soon? Was that okay? I got to thinking maybe I did. I thought there was going to be something on the side, but I guess there was. Well, let's see, there may be something on the side here. Oh, here it is. Now, this one I don't like at all, okay? I know what they're trying to say here, but I think they got they're showing vertical layers where they really should be showing at least somewhat horizontal layers. But they're showing the pushing apart and new material in between. I understand that's what they're saying, but they're not vertical. They would be like this. They would be laying on top of the previous layers, laying on top and laying on top. So I don't really care for that one, but it is telling a story that new material comes in between the old material. Okay. All right. Everybody got that one? Okay. Now, remember what the lithosphere was? Lithosphere is the rock layer above what? Another sphere. Asthenosphere. The asthenosphere is the elastic, hot, semi-liquid layer that the lithosphere sits on, floats in. Okay? So, putting this together, lithosphere plates and boundaries, here's the basis of plate tectonics theory. The lithosphere is broken into fairly rigid plates. Many of them huge, a few of them fairly small. The plates move on the asthenosphere. It's sort of a semi-liquid layer that they can move on. Your earthquakes, volcanoes, and other rapid changes in the Earth's crust occur most often at the plate's edge. Okay? I'm going to get my visual aid out here again, my good old globe, while y'all are writing that down. Has anyone ever heard someone refer to the Pacific Ocean by a rather strange name? Johnny Cash wrote a song by the same name, or at least sang. So whether he wrote it or not, I don't think he was talking about the same thing. But anyone know what basically the circle that makes the boundary of the Pacific Ocean, what that's called sometime? Ring of Fire, exactly. Was it Johnny Cash gave it away? Okay. The Ring of Fire. Why do they call it that? A vast number of the volcanic and earthquake activity in the whole world happens in that ring of fire, the fire from the volcanic activity. If you think about it, there's been several earthquakes recent off Japan. One of the strongest ever recorded was in Alaska. There's been several recently in Indonesia. Right there, ring of fire. A lot of these islands are volcanic islands, okay, including Hawaiian Islands, which are in the middle of the ring, you might say. A lot of seismic activity along the western coast of South America. Chile, Peru, they have quite a few earthquakes and volcanic activities there. In the Pacific Northwest, you can just start, even in Canada, you can just start naming volcanic mountains. The Cascades are mostly all volcanic mountains. Mount Rainier, Mount Shasta, Mount Hood, Mount St. Helens, just over and over and over, all these volcanic mountains up and down. The Ring of Fire. Okay, why did we bring that up? We were in the middle of Atlantic Ridge, I thought before. Why are we talking about the Ring of Fire in the Pacific? Well, most of the volcanoes and other rapid changes occur most often at the plate edges. Guess what? That's where the plates are. There are 3 plate motions that typically occur. We talked about one in the Atlantic. This is divergent, moving apart. There's another that's convergent, crashing together. And then there's another one, and it's called the transform. They're moving, sliding past each other. Sliding is not a good word. Grinding past each other would be more like it, okay, under a lot of pressure. So those form the plates and the boundaries. And here's that picture we saw way early. These are your major plates as we understand them now. big old Pacific plate, and the boundary of this is almost a ring of fire, okay? Not quite, okay? You combine some of them together. But the Pacific plate here, the North American plate there, there's a Nazca plate that's it's separate from the Pacific plate, and a lot of activity is along that, so the ring of fire includes that boundary as well. There's the Caribbean plate sort of stuck in between the North and South American plate. And you notice there's no Atlantic plate like there's a Pacific plate, because the Atlantic plate, half of it's with, or a quarter of it is with the North American plate, a quarter of it with the South American plate. See, this part is underwater, but that's still we're part of the same plate. Then the African plate, about a quarter of it is with the African plate, and a quarter of that is with the Eurasian plate over here. See, this is underwater, okay? So there is no Atlantic plate because that's part of the continental plates there, okay? This is the other part of the African plate. Here's an unusual one. This is the Indian-Australian plate. We think of India as being part of Asia, and it is, but it's not on the same plate. Eurasian plate is up here, the Indian-Australian plate, they're on the same plate. A lot of it's underwater, but they're on the same plate. And remember the big tsunami that hit India and other places as well, right around Christmas. It must have been 15 and 20 years ago. Do you remember anything about it? Okay. It was mostly the eastern shore of India. Are you from the west? Okay. You're from down here, kind of, aren't you? Okay. I know the name like that. Ceylon got hit, or Sri Lanka got hit pretty badly by it too. We have friends who have a lot of family in what used to be called Chennai now. It used to be called. But anyway, back then it was called the other name in Tamil Nadu. Madras, yeah, it was called Madras. They lived in Madras, but it was close enough to the ocean. They had family members that were on the beach that day, and when the tsunami hit, they all, I think, lived. I think maybe they did lose a distant cousin or something. But anyway, from being on the plate boundary. Okay, but India is actually on the same plate with Australia, not the same plate with the rest of Asia. Rather strange. Then there's the Arabian plate here. And see, the Red Sea is that boundary. I pointed that out earlier. It's a plate boundary. The Mediterranean is a plate boundary between Africa and Eurasian plate. So yeah, a lot. And then down here is the Antarctic plate. Now that looks huge, but it's that. I mean, it's not that big, but when you spread this out into a flat globe, it looks huge. Anyway. But those are approximately the plate boundaries. Now, some of these plates are moving apart, like in the Atlantic along this. That's the Mid-Atlantic Ridge. That's the divergent plate. Some of them are crashing together. That's usually the Nazca plate against the South American plate. Okay, and that's where a lot of real strong activity is going. In fact, when you run your finger along this, you find a huge ridge right here. That's the Andes Mountains. Okay, they start in northern South America, maybe even up here, go all the way down, almost to the tip, and they are formed because of those plates grinding into each other, pushing the mountains up. And that's why we have the Cascades and the Rocky Mountains a little bit, more of the Cascades. Oh, I'm sorry, I'm wrong time. Ours are not as marked, but the Cascades and the Sierra Nevadas are doing some of the same type thing here, much more pronounced down there. Okay. Now, northern India, Nepal, what's up there? Second? What's up there?
Himalaya.
Himalayan mountains. Guess what? They're the boundary here. Those two plates are hitting each other, and that's forcing up. The Himalayan mountains are still growing because those plates are moving closer and closer together. They're grinding into each other. So those are convergent plates. There are also transform plates moving past each other. It just happens to be along here, the plates sort of are moving this way toward each other. Somewhat converging, but more of a transform. Okay, so let's look at these three individually. The divergent boundaries. These occur between two plates moving away from each other. Generally, the molten material from the mantle rises to fill the fissures that are opening up. Okay? Now that would be, when they say from the mantle, that molten material mostly from the asthenosphere. Remember, it's semi-liquid. It has liquid in it, so that's where. And that's why it's coming up at those plate boundaries, okay, to fill the fissures. That's why Iceland is where it is. The molten material has come up there. You create new crust zones. What was mantle material is now becoming crust material because it came up into the crust. Often accompanied by volcanic activity. Iceland, Hawaii. Boy, remember, was it last summer or summer before that Mount Kilauea was just erupting like crazy? It's always been erupting, but boy, it really picked up last summer. It was either last summer or summer before. And I mean, just moving right along, creating new crust material, but of course not destroying, but burying the crust material that was there. The biggest example here is the Mid-Atlantic Ridge, but we'll see in the last chapter we get to that there are other ridges out there besides the Mid-Atlantic. Okay? And this is basically what we think is happening. Here's the asthenosphere. Now, they show it way too thick here, but it's come really close, and the lithosphere, which is magma and crust, this is magma, that's crust, has gotten pretty thin here, and here is where the asthenosphere, the materials from that come up and boil over. This is under the ocean mostly, and boil under the ocean and create this ridge here. And that video I saw just showed that boiling lava coming up, just spewing out there, pushing the edges further apart. Very little, but still doing. So that's the source of most of our magma is from there. Now, actually, the picture is not bad here because it's near the boundary of the lithosphere. Okay, I mean the mantle. Okay, there's chunks of rock in this too. So when you have volcanic activity, a lot of it's liquid, but you also have pieces of rock coming out into that too, and that's why we know it's olivine that's down there in the mantle, because it comes up with the volcanic material. Okay, those are your divergent boundaries. Convergent boundaries. Okay, these occur between two plates moving toward each other. Now, in this process, whereas in diverging, new crust material is being formed. At convergent boundaries, you're destroying crust material sometimes, not always. All crust material is sometimes destroyed in the process. This occurs when the two plates move toward each other. Now, here's how you destroy the old crust material. This is mostly oceanic crust. Okay? If you think about it, the Mid-Atlantic Ridge is creating new oceanic crust there. You're losing oceanic crust in some of the other areas. What happens here, one crust is subducted under the other. And remember that figure that I showed you? Early on I said they drew it curving up. It should have been curving down. That's because the denser crust typically goes under the less dense crust. So, and we'll talk about the three types in just a minute. But the belt The subduction zone is a belt where one crust goes under and the other. The subducted material gets pushed further and further down, and at some point it hits maybe the asthenosphere somewhere, and it turns back into molten material. Now it's part of the mantle, not the crust anymore. Actually, it became part of the mantle earlier and subducted under there. It melts and joins the mantle again. So what was crust, because it's being forced together, it ducts down under the other crust, and it becomes part of the mantle again. So here's three possibilities of converging situations. You have converging continental oceanic plates, you have converging oceanic plates, and you have converging continental plates. Okay? Three possibilities. Let's look at each one of those separately. I'll leave it up there a little bit longer. Okay? Just to give you a heads up on it. Remember, what is the continental plates made up mostly? Anyone remember that? It was only an hour or two ago. Continental plates are mostly what kind of rock? Let me give you a hint. Light-colored, igneous, coarse grain, large crystal size, most common. We make countertops out of them. Granite. Okay, finally got it. Okay, so it's lighter colored, but it's also lighter density because it has less iron in it. So those are light. The oceanic plates are what mostly mineral? The B word. The salts, exactly. Darker, denser, those are heavier. So guess what's going to happen between a continental plate, light granite plate, and a thin, dense, heavy oceanic plate? Who's going to be on top, who's on bottom? Yeah, the granite goes on top and the other. That's why I said that earlier figure that showed them curving up or not, the oceanic plate curves downward. Okay, if it curves at all. Okay, everybody got this one finished or not yet? Okay, I keep interrupting. Now with the oceanic plates, I don't know who determines who wins that one because they both tend to be basalts. But one of them has to go on top and one on the bottom. Maybe it's just historically how they were first came together. Who knows? Okay? But boy, the converging continental plates tend to both be granitic type materials. Where have they got to go? None of them goes under, they just go up. And that's why the Himalayas are growing. Okay, so let's first look at oceanic continental plate convergence. The oceanic plate is a denser basaltic material subducted under the less dense granite type continental shelf. That picture I showed you before, it showed the oceanic plate sort of curving up. No, it curves down. It subducts under the continental shelf. Let's see if there's a picture of that. Yes, right there. The oceanic plate, the basaltic plate here, it subducts under the continental granite type plates here. Is that a smooth transition like it shows here? Anything but. There's no reason to think the oceanic plates are smooth and rounded. No, they're rugged, sometimes even mountains. We'll see this in a later figure. And when they are scrubbing underneath, the pressure, the force that's happening there is enormous, and there's a lot of friction, and somewhere down there, the friction actually starts melting the mantle material. And when it does, if that molten material can find a break, and this can cause some problems in the crust here, all that grinding going on. If it finds one, there the high pressure magma comes up and you have a volcano. Okay. And what happens? Remember when we said there's these trenches right along the edge of the continents? This is why. That's where the oceanic plate subducted under the continental plate, leaving a trench. Here the depth of the water was fairly uniform out here. It took a dive as it got closer to land before the depth of the water started rising again. I mean, the surface started rising again. This is why the trench is there. We knew they were there. Now we see why they're there. Okay? So they're marked by these oceanic trenches. Deep-seated earthquakes down here. Way deep. It's really deep into the mantle where those are coming from. Now, we will classify earthquakes in a couple chapters from now, but remember, these are deep-seated earthquakes. We'll see that later. And, ultimately, forming volcanic mountains. And a lot of your coastal mountains are volcanic mountains, especially on the west coast. Shasta, Rainier, Fujiyama in Japan, Mount Hood, Mount Baker, all those are volcanic mountains, okay? And all up and down the Andes. Tall mountains, a lot of them volcanic. Many of them old volcanoes, not active anymore. But guess what? Mount St. Helens used to be an old inactive volcano until, maybe 30 years ago, it suddenly erupted, maybe 40 years ago. Suddenly erupted and spewed stuff everywhere. Okay, one of the examples, the convergence of the South American plate with the Nazca plate. If you'll let me flip back a few slides, I'll show you where that was. Right here. Here's the Nazca plate, and here's the South American plate. And like I just said, the Andes Mountain. Very, very tall mountains, all up and down the spine of South America. And you can almost tell exactly the boundary of that Nazca plate here if you run your finger along here. Up here it's less so, but here is where that Nazca plate is. Oh boy, those mountains are far up there. Here it's just a little bit of a rise, and we think those are tall mountains. Nothing compared to the Andes. South America. Okay. So let me get back to where we were. So, any questions on ocean continental plate convergence? Who winds up on top? Which plate? Earth to class, come in please. The continental plate is on top. It's lighter, less dense. The oceanic plate, basalts, they get subducted under. And that's where we lose the plate. When it goes far enough down, it becomes part of the mantle again. No longer the Earth's crust, back to being the mantle. You see the same thing we talked about in the last chapter. Everything goes in cycles. Some of these cycles are really slow and long, but they still go. Okay? Now, let's do ocean plate convergence. Now, when these happen, you get some really deep trenches. Okay, we just passed 315. How are we doing as far as the chapter goes? Oh boy. We can't finish anytime real soon. So I guess what we'll do is just keep on trucking through chapter 18, and then we will have time to start 19. And then on Tuesday of next week, first 2 hours we'll continue 19. Next 2 hours we will do the lab from this one, 18, and then the last 30 minutes we'll do the test on 18. So it doesn't look like we're going to have time for a lab today, so we'll probably continue on 18 till we finish, and then start 19, and then stop in time for the test for 17. Is that all right? Okay. Okay. So with ocean-ocean plate convergence, you got two similar plates, both basaltics, both way under the ocean. No one has an advantage, upper hand, you might say, but something has to go down, something has to come up. So these are associated with deep-seated volcanoes, and a deep, deep trench is created way underneath the water, and an underwater ridge could be created as well. The island arcs form where the melted subductive material rise above the sea level through the overriding plate. Okay? In other words, the volcanic activity that you have here forms these island arcs where the plates, sub-oceanic plates, were colliding. One such group of islands is the Hawaiian Islands, and you see it's one large arc of islands. Now that extends way past the main ones we think of a lot, Hawaii, but goes up here. You can just turn the globe to the Pacific and you'll see arc islands everywhere. Actually, New Zealand is an arc island. Most of Indonesia is an arc island, right on the boundary of the Pacific Plate and the India-Australian Plate. Arc islands here. Look at, this is again part of Indonesia. Look at that arc. Boy, you see? Very definite arc islands there. Look at Japan. Japan is one string of arc islands. Okay? And Japan is almost all volcanic material. Almost all volcanic material. Look at the Aleutian Islands. You ever see an arc much better than that? Okay? Again, plate boundaries are subplate boundaries. You can almost extend the Japanese arc into the Kuril Islands and into the, I can't know how to pronounce that, Kamchatka Peninsula here. It looks like it's just all one big arc. And you just, here, the Polynesian. Some of these are so many it's hard to pick out, but here's the Marquise Islands, here is the Line Islands, over here are the Ratak chain, here is the Relief chain, here are the Caroline Islands, they make a chain this way. Oh, the Philippines. They're on the boundary of two plates, and they form an arc island. They're almost totally volcanic material. Okay? Anywhere in the Pacific, you can just find these chains of islands. Okay? That go along. Here's the Samoan Islands, the Kiribati Islands, Body Islands. You know, all over the place. Those are island chains. Okay? Those island arcs, I call them chains, they call them arcs. Arcs form where the melted subductive material rises up above sea level through the overriding plate, and they form these arc island chains. Arc island chains. One example, Japan, another Hawaii, there's a bunch of them. Okay, here's the illustration of this. Here we have an oceanic trench, okay, the oceanic crust. Now the picture here indicates this one may have originally been a lot thicker, maybe originally, I don't know, it's hard to say, but where this one started subducting under, then it formed volcanic activity here, deep-seated earthquakes and volcanoes coming up, and you'll have whole strings of volcanoes here, some of them beneath the sea, some of them above. Where they're above, they form islands. Where they're not, you don't see them, but I bet you there is a link there. They're just underneath the water. So these form the island arcs. Over here, you have your deep, deep trench. Now, I was looking for, I never saw it, but I'm going to point it out to you now. We'll talk about this in a later chapter, too. There we are, the Marianas Islands, okay? They are an arc island chain, okay? And on one side or the other, I think on the outer side of that, you have the oceanic trench, the deepest part of the ocean anywhere. The Marianas Trench is called. Guam is one of those islands. I've actually been on Guam, but there's several others in that chain. Arc. Okay. And now we come to continent-continent plate convergence, the third type of plate convergence. This time, you have less dense granite-like materials resisting subduction. They're big, thick, low density. They really don't want to subduct, and it's hard for them to subduct. So guess where they have to go? If they can't go down, they go up. And this is where you have colliding plates pile up, producing a deformed and thicker crust of lighter materials. And the big example of that is the Tibetan Plateau and the Himalayan Mountains. The Himalayan Mountains, the tallest mountain chain in the world, and still growing. Okay? Believe it or not, I've read or heard this somewhere before, it was thought at one time the Appalachians were one of the tallest mountain chains in the world. But guess what? They've been so inactive for so long, and we're going to talk about this in a later chapter, more folded mountains, not volcanic mountains. So they basically, the pressure's eased off, and the Pacific picked up, so the Rockies are way, way taller than the Appalachians. Andes even taller than that, and many of the places here. But the Himalayas top them all, and that's because it's not oceanic continental, it's continental. And here's the Himalayas here, big, steep, tall mountains here, and the Tibetan Plateau is above them. And that's been raised. Mount Everest, the tallest mountain in the world, and I think something like the 5 tallest mountains in the world are right along that thing. Mount Everest is just one, but there's several others. Some of them, they just number them. But they have some of the names listed here too. Huge, huge mountain. That's continental plate convergence. Okay? Should be a figure here. Yeah, this is showing what's happening here. One continent coming this way, say the Eurasian plate coming this way, the Indian, Australian plate coming this way, forming together. They can't go below or thing, so they just pile up. It's like if you've seen where train wrecks happen, sometimes the cars go up, into the air. And it happens some in automobile things. If there's a huge thing, some actually wind up going up. There's nowhere else to go, and they wind up climbing up. That's what happens with a continent-continent plate conversion. That's where you get mountain formation. Any questions? Okay. The third kind of boundary, we have divergent boundaries, convergent boundaries. The third type is transform boundary. These occur when two plates, and I don't like the verb slide. I like the verb grind past each other. It's not a slick slide at all. It's grinding past each other. The crust is neither created nor destroyed in the process, but irregularities in the movement along the boundary cause for problems. Some of these problems are the sudden jerks, not referring to anyone in particular, that produce earthquakes. Just imagine, and remember, none of these boundaries are slick or smooth. They are jagged, rugged, rough. And if these plates are trying to slide past each other, and this one has a boulder sticking out here, and this one doesn't have a place for it to go, they just build up pressure, build up pressure, build up pressure, build up pressure until something happens to make it break. That's an earthquake. Guess where one of the most famous of these transform boundary is? where are most of the earthquakes in the continental U.S.? California, here I come, and that's the San Andreas Fault along California's coastline. Now, they say coastline. Parts of that are pretty far inland, okay? And we'll show a picture of it later, but I'll let you finish getting the slide. The San Andreas Fault. Guess what city is almost on top of that fault? San Francisco. Back at the turn of the 20th century, it's either the late 1890s, early 1900s, sometime in there, there was a major earthquake in San Francisco. It really wasn't all that big, but it was so damaging because San Francisco, just remember what happened in 1849? The 49ers? Gold Rush. And San Francisco went from being just a little spitting pocket sitting there to being a major city. It was built fast, it was built poorly, mostly wood structures. They had a lot of wood out there, built those. And then by the 1900s, they had this earthquake. Gas lines broke, fires broke out. It was devastating. Major earthquake in San Francisco. Now, more recently, maybe before y'all were born, but not too much. I can't remember what year, maybe 89 or something like that. May have been around 89. There was another earthquake in San Francisco. San Francisco was much more safely built and things like this, but still, this earthquake, no, you don't mess with Mother Nature. Of course, there's, I don't know if y'all are familiar with San Francisco, but the San Francisco Bay. You really can't see it on here well, but there's just little peaks of land that are connected by the Golden Gate Bridge. If you go under the Golden Gate Bridge, and that's the San Francisco Bay. Alcatraz Island sits in the northern part of that bay. It curves down around San Francisco, down, oh goodness, I can't think of names. It's Palo Alto. Okay, that's what it is. In different areas there. Oakland's on the east side of the San Francisco Bay, and San Francisco's on the west side. San Francisco's on the sort of peninsula. Well, that year, I think it was 89, the winner of the American League Baseball was Oakland Athletics, I think they were. The National League winners was the San Francisco Giants. So they played each other in the World Series. And it was called the Bay Series because one was on the east side of the bay and one was on the west side. Those two teams didn't have very far to go to travel between the games. But during one of the games in Candlestick Park, was the park then, it's now something else, the game was going on, and suddenly there was an earthquake. And it was a major. Now, I mentioned San Francisco Bay. From the Oakland side, there's another big bridge called the Bay Bridge Tunnel. Okay? It goes across part of the bay and hit Yerba Buena Island, which is a little island there, but went up pretty high. And then they did a tunnel through Yerba Buena Island and then came out on the other side and had another bridge going on to San Francisco. So the island was about in the middle, and that's where the tunnel came from, the Bay Bridge Tunnel. The bridges on either side of the tunnel underneath. I think it was mostly on the Oakland side where the earthquake was. Oh, I did mention this. The Bay Bridge had 2 lanes of traffic. I can't remember which one went eastbound and one went westbound, but they were one on top of each other. They weren't side by side. They were on top and bottom of each other. I think when they got to the tunnel, they spread out, but on the bridge part, they were on top. And I think at one time there may have even been a train track that was underneath those. But I know at this time it was 2 lanes of traffic. When that earthquake hit, even though things had been built very carefully to earthquake standards, wham, the top level of layer of traffic went down to the bottom layer. There were cars crushed. It was near rush hour, so the Bay Bridge Tunnel was packed with things. The earthquake hit, collapsed it. It was not pretty. I don't know what the loss of life was, but it was probably pretty significant. Okay. Within, I'm guessing, a few months of that, but certainly within a year or two, there was another earthquake down near Los Angeles. And that's way south of this. And they said it wasn't anything connected with it, just happened to be close in time. But there, they showed things of interstate highways just collapsing onto the roads underneath them. Even though they were built to very stringent earthquake standards, you can't mess with an earthquake. It's way stronger than anything we could build all along the San Andreas Fault. Okay. What's our present day understanding of what's happening? We know it's happening. We know all the evidence, or at least the theory, is that the plates are moving. And that's why you have earthquakes, why you have volcanic activity along them. We know that the subduction occurs. We know that the Himalayas are growing. We know all this stuff, but what no one's figured out yet is why. What is driving the plates? Why aren't they happy just to sit next to each other, okay? Why do they have to grind into each other? Well, there's a few current working hypotheses. They say one here, but there's actually several. And one of these is convective cells in the asthenosphere, okay? And we'll show you the figure and try to tie what they're saying in with it. I guess what they think is happening is the core is down here, and boy, it is ever hot. I mean, the friction is just incredible. Liquid rock at huge pressures is still liquid. It is hot, hot, hot. Well, that creates, and maybe there's little weaknesses in the mantle, I don't know, but you get the convective cells, that hot material coming up, even if it's not liquid material, but it's the heat coming up, and happens to be hit, say, in the middle of the Atlantic, is where a string of these are, and that hot material is pushing. So what they say, convective cells in the asthenosphere. So this is showing the whole mantle. It's mostly in the asthenosphere. The hot fluid materials rise at the diverging boundaries. Well, to me, this begs the question, why is the diverging boundary there in the first place? That's the part I don't know. But they say rise. That makes sense. And maybe the mantle is thinner there. Maybe the crust is thinner there. Surely it must be, because you have a diverging boundary. So anyway, for some reason, these convective cells are pushing their ways up, and that the hot fluid materials rise at the diverging boundary. Some escapes to form new crust. The remainder spreads beneath the lithosphere, down here around the asthenosphere, pulling the plates apart. Remainder spreads beneath, dragging the overlying plates with it, and this starts the cascading effect. Okay? The problem is you got little supporting evidence. This is just a working hypothesis. Well, it seems to work, but what starts the process? We don't know. But if indeed that's happening, then the oceanic plates, which are subducting under the continental plates, if they are subducting there because they're being forced here, or for some other reason, then gravity may be pulling them down. And you call this, the one's a push and one's a pull. So this is pulling down, and where it's grinding past the continental crust or the mantle, you create earthquakes, shallow earthquakes, mid-earthquakes, or deep earthquakes. Okay? Or on the oceanic side, for some reason this oceanic plate subducted under that one, and then that creates all the problems there, and you have the pull here that's pulling the plates further apart. They don't know. These are all theories. We know it's happening. We see the evidence of it is happening, but we don't know why. And by the way, this is a pretty good picture of why you have the island arcs and why you have the oceanic trenches. You have them in the middle of the ocean and near the continents as well. Okay. But not in the Atlantic, because the Atlantic are part of the plates that are there already, and all they're doing is spreading apart. There's no trenching going on in the Atlantic, so there's just the ridge there. That's why the Atlantic Ocean, if you've ever been to the beach in the Atlantic, you know you can go out and out and out, and you're still in shallow water. And you might hit a place where it goes deep, but you keep on going, and then you find the sandbar. And you can just go way, way out there. It's called the continental shelf. We have that in the Atlantic. In the Pacific, it just plummets down to that deep trench. So that's why there's some differences between the coastal oceans. All right, any questions? That's it for chapter 18, sorry. Now, we're right at 3:45, which is our break time anyway, but there's no lab today because we have a test the last 30 minutes. So what I think we'll do now, wait, before I turn anything off, there are some illustrations in the book that's a little different from the ones that were here, but then there's also a measuring plate movement. This is a really interesting blurb here. They have actually measured the movement. It's incredibly slow, about 10 centimeters a year. That's between 0.2 of an inch to 4 inches a year. 0.5 to 10 centimeters, which is 0.2 to 4 inches a year. That's awfully slow. So you can read about some of the ways they've been able to measure that movement. There's also some examples here of earthquake data that, again, you almost need to have the knowledge from the first half of the book to do some of this, but it's pretty interesting to read. So I'll let you take a look at it. Then there's a myths, mistakes, and misunderstanding, and this is one that's really kind of, I almost want to say funny, but it's not really funny. It's just bad ideas. Actually, it was a presidential candidate. Goodness, where is that picture? Oh, it had to have been after that. Let me keep going. No. I think I went right past it. There it is. Okay. By the way, here's the San Andreas Fault. It goes inland for a little ways. Okay? Okay. I think I may have mentioned this when we had it. In a later chapter, we're going to see a picture of agricultural farmland right on that fault. And it's pretty amazing. Right after one of the earthquakes. It's worth waiting for. Okay? There was something else that came to mind. Oh, yes. And this is what led from it. Because of the earthquakes along there, and because of Hollywood. How does Hollywood picture earthquakes? The ground separates and people and trucks and cars fall in, right? Never happens. Never happens. The earthquake is a shaking. The effort has been way, way down deep. You just get shaking like crazy. You may get a little bit of movement, but it's not any gaping holes. Ever. That's Hollywood. But someone said one time, I think it was Barry Goldwater, it wouldn't be a bad thing, this was way back, ran against Lyndon Johnson in 68 or something like that. He said it wouldn't be a bad thing if California broke off and fell into the Pacific Ocean. He didn't like California so much. He was from Arizona, by the way. But anyway, not going to happen. Earthquakes don't happen that way. They don't break apart and one piece falls. The person behind the science, pretty interesting character to me, Harry Hammond Hess. Talk about alliterative name. He was a naval officer, and he was a scientist, geologist, and he spent most of his naval career mapping the bottoms of the oceans with sonar and other techniques. And due to his efforts, we have a lot of data about the oceans we wouldn't have had otherwise, including some of the core data and other stuff like that. Then there's a Science and Society of Geothermal Energy. I mentioned Iceland. We have a few places here in the U.S. California has 10 sites. Hawaii and Nevada have 10 sites. Oregon and Utah, 2 sites each, where they get quite a bit of their energy from the earth, not from burning anything, you know. And anyway, some of the others, I couldn't think of the names, the slab pull effect, and there was another something push, crust push effect or something. Like I say, on every chapter, nothing replaces reading the chapters. Please read them before I talk about them, then maybe go back and read them again or skim through them again afterwards to pick up anything else you may have missed. The summary here is a pretty decent summary. It's a bit shorter than most. The key terms are definitely shorter than most. And the applying the concepts, they have 52 questions, which is more than most. So that's, to me, the best thing to study for the test. Okay? Then you have questions for thought, 16, and for further analysis, 24. 4. Okay, sorry, 4. I was adding them together in my head. That's where 24 came from. Now, they have the Group A and Group B parallel exercises. You don't need to mess with those. They're more like those examples that we didn't really do. But if you want to take a look, you certainly can. And here we have the 10 o'clock scholar. Gotta find you. I know you're in here. Seth is here. And let's see. I believe you're into the lab period, though, right? Okay, so you missed the class period. Now, though we're not having a lab today, but yeah. All right. Now, I do want to stop here for just a moment. Even though we're not going to do the lab until next time, if you want to start your lab, you can do this. And here's why. The lab for next time is only 10, it's not even 10 questions, 10 pieces of evidence and conclusions. That leaves 15 to go. So here's what you do for your other 15. Notice I said questions for thought at the end of chapter 18 on page 478. There's 16 of those and 4 for further analysis. That's a total of 20 questions. You can do 15 or more of those questions. That's what you're going to have to do for your lab. So if you want to get started on those now, that makes your lab easier for later. The other thing it does, great things to do before we take the test next time. So I would say, even though we're going to do the lab first, you're not going to have time to do 20 questions or 15 questions or however. But I would say between now and then, start working on these questions. Great study tool. Okay? So start working. Do 15 or more of those 20 questions. There's 16 questions for thought and 4 for further analysis on page 478. Start working on those. Do any 15 or more. Yes?
You said those questions are going to be the lab? You said those questions are the lab?
They are part of the lab. The first part of the lab will be 10 points worth. We're going to do that in the lab. We're going to actually do a wet lab this time. We are actually going to go down to 259 and do a lab down there. If we can't do it in 259, we'll go to one of these other labs and do it, 253 or 251. One of those, or no, 252 or 253. We'll go to one of those labs and actually do a lab. That's only 10 points worth. The other 15 points are from these 20 questions. And you can do more than 15 in case you get something wrong on the other part. You can still get your 25 points for here if you do extra questions. Okay? You can do all 20 if you wanted to. Great thing to do to study for the test, but you don't have to do it. So I would suggest you got a weekend ahead of you. Why don't you take advantage of it and start working on those questions that are going to be part of the lab. And then when we do the lab, if you already got your questions done, you can turn them in. Okay? Any questions on that?
What's the page number?
What's what?
Page number?
That's page 478. All 20 questions are right there. 16 questions for thought and 4 for further analysis. Okay. I had meant to finish this sooner, but let's take a quick break. Let's say 5 minutes or less, and then we'll come back and we'll get started on chapter 19. And we'll only go for about, it's less than an hour and a half now, because at the end you want time to do your test of chapter 17. So that will be the rest of it. Chapter 19 follows directly from what we did this chapter and the previous chapter. They really tie together well. So I'm going to turn off this for now. Now, any questions from chapter 18? Okay. Things are going sort of fast and furious here. 30 minutes before the end of class today, we'll have the test on 17. We just finished 18. We're starting 19 but last time we had the lab for 17. So next time we'll finish 19, or hopefully get onto it anyway. Then we'll have the lab for 18 and then the test for 18. Okay. The lab for 18 won't be super long because, like I said, it's only 10 points worth, but there is some actual activity. You'll be measuring things, weighing things, doing a variety of things like that. And then the last part of it will be answering questions. So the more questions you get done this weekend, the less time you have to spend in lab on Tuesday doing questions, and the better you'll be studied and prepared for the test coming on Tuesday. So it's really beneficial to go and get started on those questions this weekend. Today, tomorrow, the weekend, and Monday. All right, so we did finish. Sorry, I forgot that I went back and showed you something, and I forgot. Okay, whoa, yeah. All right, let's move on to 19. Okay. We'll start from the current slide. All right. I said this is a real close tie to what we did in the last chapter. It's continuing now. This is building the Earth's surface. Now, in some senses, it's very similar to what we did because we talked about the crushing of the two continental plates together, building the Himalayan mountains and other mountains. The Rocky Mountains are still growing because of forces upward. They're not exactly the same phenomenon, but similar to what the Himalayas are doing. The Andes Mountains are still growing because of the subduction of a crust underneath it, pushing them upwards, also causing volcanic activity. So we'll be talking about that kind of building as well as volcanic activity, which we mentioned in the last chapter. That builds the Earth's surface. But other forces that push up on the Earth's surface. And here is the core concept here. If this sounds familiar, it should. The surface of the Earth is involved in plate tectonic processes, that was the last chapter, that result in an ongoing building up of the surface. Now this is a picture, I'm pretty sure, of Mount Shasta, which is a massive volcanic mountain in Northern California. Beautiful mountain, as you can tell. Way high elevation, so it gets a lot of snow cover, I think almost all year long. You can see the lava flows from when it was a volcano. There's part of the crater, I believe, right there. But it's been dormant for as long as we've been around. And but at one time, obviously, it was an active volcano. And it's right there near where the Nazca Plate or the Pacific Plate one, probably not Nazca, oh my goodness, I think it's Pacific Plate, but it could be the one, the Fuca Plate, is pushing under the North American Plate. But you see, really, that's more of a transformed boundary now. Maybe at one time it was a converging boundary, oceanic, continental, and that may have been when this was more active. And now it's gone more transformed, so it's not being as active along there. Though Mount St. Helens is in that same range, but that certainly at one time was being built up. So this chapter, the building of the Earth's surface, building up, ongoing building up of the surface. Now, next chapter, we'll talk about how this surface is being worn away. So that's the other side of the coin. So, first topic here, interpreting the Earth's surface. Okay? Now here is, it started with the rock cycle and has been continuing ever since. This is called, a slightly different name, the principle of uniformity. And a shorthand way of thinking of this, the present is the key to the past. Now, that somehow to me doesn't carry a lot of weight, or I don't know what they're talking about at first. So let's jump down to the bottom of the slide first. Okay? The bottom of the slide indicates what people used to think. They used to think there was a whole series of catastrophic events that went on that formed the Earth, and then since then we've just been muddling through. Okay? Principle of uniformity says no. What's happening now was also happening back then. There's no reason to believe there was just a whole series of catastrophic events that created things, and then things have just been eased off since then. Before, they thought volcanoes were erupting like crazy, earthquakes were happening all over the place, meteorite impacts were happening. We're sure in the very earliest time of the Earth's formation, way back here, yeah, there were more meteorite impacts because the Earth has just been formed. But we weren't around then. We weren't anywhere close to being around then. Okay? Europe, probably there were more earthquakes and volcanoes sometime back in then. But basically, what's happening now has been happening for a very long time. Rocks are changed today by the same process that changed them in the past. Igneous rocks are being formed from volcanic activity. Sedimentary rocks are being caused by sediments. Metamorphic rocks are being metamorphosized by the same heat, temperature, pressure, and time that they were in the past. They were then, they are now. So this replaced, the principle of uniformity replaced the catastrophic models of previous thinkers. They thought everything's sort of stable now, it used to be really in flux. No, it's always been in flux, it's still in flux. And things like your bottom of page 482 is a picture, 1982 image of Mount St. Helens that's fairly close to, between Seattle and Portland, Seattle, Washington, and Portland, Oregon. Mount St. Helens is the most notorious for its eruption on May 18, 1980. So this was 2 years after the eruption. And look, it's still venting some steam every now and then. The eruption is long past. Now, if you take a look at that crater that you see there, and in the middle of the crater you see a little mound. That's where it's sort of forming a new volcanic flush. But actually, when it blew the side of the mountain off. Now, I guess I had always thought when a volcano erupts, it builds because the new material comes up and goes down the side, new material comes up and goes down the side. Well, actually, Mount Helens lost elevation because it blew the side and top of the mountain off. It had been plugged up that long, that much force, blew it off. And yeah, new volcanic material went down the sides, but not enough to make up for what it lost. So here you see what's left over 2 years after the effect. When it became the deadliest and most economically destructive volcanic event in the history of the United States. 57 people were killed, 250 homes, 47 bridges, 15 miles of railways, and 185 miles of highway were destroyed by that one eruption of Mount St. Helens. Now, I was, let's see, how old was I? It was 80, no, this was 1980. I was 19 years old. Is that right? Or 29 years old? 29 years old. I remember it. I remember it. I didn't know that many people died. I didn't know that much was destroyed. Actually, there was, when it says the economically destructive volcanic event, there were great farms fairly close to the mountain. There were trees all over the sides of the mountains. And when that lava came down, I mean, it started fires that were major. And it wiped out lots and lots of farmland. I remember hearing about all that, and you think, oh, how disastrous for those farmers. And it was. I mean, it was pretty major. But within a few years, when they planted more apple trees and things, they had some of the best crops ever because they had fresh, new earth with lots of minerals right there. You know, so the earth, this process of uniformity, what's happening now, happened before. This was making new soil, new everything, so it's not a total loss, okay? This leads to another concept, and this is the diastrophism, which is a really hard word to say, for me anyway. The process of deformation that changes the Earth's surface. When you see the root, or the root word troph, that usually means change. So this is pretty dramatic change, I think is what that means. Dias usually indicates something changing from one thing to something else. The process of deformation that changes the Earth's surface. Now this produces structures that we see, and they have various names: plateaus, mountains, folds in the crust. So this is the process by which this happens. It's related to volcanic activity, that's volcanism, movement of magma, and earthquakes. That's certainly part of diastrophism, but it can be involving other things as well. The basic working theory is plate tectonics. Okay. Now, these are almost sound like catastrophic events, but some of them don't sound like catastrophic. Plateaus. You certainly think of this as a Western word when you have the plateaus out west, and there's flat areas that surrounding those that are either fairly steep or mountainous or something, then you hit a sudden flat area. We have some here. Right across the Chattahoochee River from Alabama into Georgia is a plateau called the Fort Valley Plateau. And some of it comes into Alabama as well. I believe probably, I can't think of the name of the town. A friend of mine grew up there. Formed a real short name. But anyway, I think probably Enterprise, Alabama may be on that Fort Valley Plateau or awfully close to it. That's some of the best peanut growing area. Americus, Georgia, Plains, Georgia, those are, I think, right on that plateau. Fort Valley, Georgia is certainly there too. That plateau's there. It's great peanut growing land, just perfect for peanuts, it seems like. Then there are places like mountains, Appalachian Mountains, the Ozark Mountains, the Rocky Mountains, the Sierra Nevadas, the Andes, the Himalayas. These are all structures produced by these changes in the Earth's surface, diastrophism. Okay? All this, or a lot of this, is caused by the moving, the shifting, the activity of plate tectonics. Even when it's in the middle of a plate, you might say. Still writing here, I'm trying to talk as much as I can to let people have time to write. Okay, got it? Okay. Here are two words. They're pretty key words for this chapter. The first of these is stress. The second is strain. Now, they sort of sound similar, don't they? It's all both start with STR, okay, followed by vowels, they all both have 6 letters, so pretty similar type words, and they're related, certainly. But here's how I think of it. Stress is the verb. That's the action thing. That's what causing the strain. So strain would be like the direct object of the verb. That's what comes because of the stress. So if you think of them that way, that's how I do. That helps me. It may not help you. So stress is the force. The force tending, and it can do 3 things. Compressing, pulling apart, or deforming. All those would be things that would be happening, say, to a rock or to a structure. Compressing it, pulling apart, or deforming it. Now, if this almost sounds a little about what the plates were doing, remember you had compressional convergence, you had divergence, which is like pulling apart, and you had transforming, which was sort of like deforming. Yeah, they're 3 sort of similar concepts, but this is talking about smaller scale stuff, rocks or local structures rather than plates. So there are 3 stress forces corresponding to these 3. First is a compressive stress. Okay, again, this sounds like the pressure wave, compression, pushing things together, plates moving together, converging plates. That's our compressive stresses. Okay? Then you have tensional stresses. These are stresses that create tension, pulling things apart. Those are tensional stress, plates moving apart from each other. That would be the Mid-Atlantic Ridge type stuff. This would be more like the Himalayas being formed. Okay? Or you have shear stresses. This would be the moving past each other out of still like the verb sliding, grinding past each other. This would be San Andreas fault type thing. Okay? Where plates or structures are moving past each other. Not necessarily colliding or straight. Okay, so those are the 3 types of stresses. The forces that are creating the action. That's why I think of them as verbs. The strain is then the adjustment of the rock, the plate, the whatever, to the stress, the forces. So that's why I think of this as the action, the verb, and that's the object that adjusts to it. So this is the adjustment to stress. Guess what? 3 types of strain types. Okay? First of these is elastic strain. I don't know if you've noticed this, but I keep leaning into the board, and the board keeps bending inwards. Okay? But then it comes right back out. Lean into it, bends in, comes right back out. So far, hopefully, it's returning to its original shape. That is elastic strain. Okay? When something returns to its original shape. Now, I think most of us, I know I used to, think of elastic as being something that stretches. Well, that's not what makes it elastic. what makes it elastic is that it returns once the stress is taken off of it, it returns to its original shape. So that would be the strain that would return to the original shape. Okay. Now, let's put this in terms of a rock. Not the country, but So let's say that something, the movement of plates or something like this is remember I said on the boundary between the plates there may be a boulder sticking out there, and it is having trouble getting around it. Well, if when the pressure did remove, or whatever, if that rock returned to its original shape, that would be elastic strain. Most of the time that doesn't happen, but it could. Sometimes when it returns to its original shape, it does it suddenly, and that could be a small earthquake or a tremor. Okay. The second type of strain is called plastic strain. I don't know which came first, our use of the word plastic or the fact that plastic had this meaning. What plastics are is something that's been heated, made into a shape, and cooled, and it keeps that shape. That's plasticity. That is something molded or bent, not returning to the original shape. Okay? Molded or bent, not returning to the original shape. So let's say when they were installing this board, I think they dropped it. And when they dropped it, this happened. It got bent. They went on and put it up anyway rather than bringing in a new board. I can almost remember the guy doing it. He was a gruff old coot, and he wasn't about to go back and undo it and redo it. So, and I wasn't about to say anything to him either. He looked like he might handle me pretty easily. So anyway, that would be not returning to the original shape. This keeps returning to the original shape. That, when it dropped on it, it didn't. It had some molding or bending left over. This would also be, I don't know if any of you remember the Saturn car commercial, when they had several, but had the kid throwing his ball, or basketball or some sort of ball, and it hit the side of the car, but then the panel popped right back. And Saturn was bragging on it didn't bend as easily and dent as easily as most cars. I guess that was true, I don't know. But if you're ever in a major car accident and you get a wrinkled fender, that's plastic. It didn't come back to the original shape. Okay? A lot of bumpers these days. In the old day, if you were in an accident, it got crinkled up and it wasn't going to come back. The bumpers today have a certain amount of flexibility that they will come back a little bit. Okay? If you just sort of nudge something, rather than breaking something or bending something, it does come back. Plastic strain does not return. And then the third, and this might actually be that. It didn't actually break off, it just bent. But if that had actually broken off, that would have been a fracture strain. Now, all these things can happen to rocks. They can return to their original shape once the stress is released. They can actually get bent, molded, okay? You don't think of rocks bending, but we'll see examples of it. And you can have, in fact, you've already seen examples. Remember that nice rock, that ancient rock they had, and had all those layers that went like this? Well, that actually went under a lot of really intense strain to bend, because those layers were originally flat. And it just got gnarled all over the place. We'll see other examples of that too. Or they can actually fracture. And this is mostly what happens with an earthquake, minor or major. That could be happening. It wouldn't just be a rock or a boulder. It would be the whole plate giving way. Okay. Now, we're sort of going backwards. Back to the stress. Now we're going to talk about what the stress causes. Possible material responses to stress. You may have no change at all. Okay? All right? What I'm going to do is I'm going to ball my fist up and I'm going to hit this wall as hard as I can. Guess what? The wall exhibits no change whatsoever. My hand, however, could be badly damaged, but the wall had no change at all. So that is one response. If the stress is not hard enough, not major enough, or much less than the wall is able to handle, no change at all. Okay? Or you can have an elastic change with recovery. I push on the board, it comes right back. Okay, that's the elastic change, but it recovers, comes back to its original strength. Or plastic change. No recovery. It got bent, wrinkled, dented, something, and it doesn't come back. And that can happen to rocks. Or it actually breaks, which that looks like it almost did there. Okay? Maybe that was my hand when it hit the wall. Okay? It actually broke. Okay? I'm not going to, but it could happen. Now, why would rocks have these four very different responses? Okay? Well, the rocks may have several different variables associated with them. Now, you already know some of these from your mineral lab that we did last time. Remember the Mohs hardness guide? Some of those were very, very hard. You may take a hammer and wham on it and nothing happens. Others of them may have fractured. Some of them may, there's other things. So you see the rock variables. One is the nature of the rock. Is it a very strong structure like diamond? Maybe your granites, maybe your iron ores, something like that. The nature of the rock would determine which of these is going to happen. Okay? Now, there are other characteristics, maybe a very hard rock that may be very, very brittle. Remember that calcite? You saw samples of it. It was associated with carbon. It was the very first mineral you did. Really beautiful crystals, big old crystals, some of them, very distinct planes. The cleavage was really obvious, okay? But it was very brittle. So just a little bit of activity, you could break that crystal to pieces, okay? So the nature of the rock, even though it may be hard, but calcite wasn't hard, it could still be very brittle. But here's a key, the temperature of the rock, okay? Now, are any of you, or maybe any of your families, associated at all with the steel mill activity in our area? Not okay. If you imagine what's going on there in the steel mills, there's a lot less going on now than used to. I guess they're still producing something. But they heat that, basically ores or whatever they're dealing with, to extremely high temperatures, and then they can mold those into whatever they want. They can roll them into sheets, they can make them into blocks, they can do other things, because the temperature of the rock determines what's happening here. You can, if you heat it up too much, you'll probably have plastic change. Yeah, because you heat it up, you can mold it however you want to, then when it cools off, it's fixed in place. Okay? You could also think of this. Now, this is a really terrible example, but I've heard it said before. Has anyone ever heard of liquid nitrogen? Have you seen anybody play with it? Hopefully not play with it. It's, huh? Okay, are you, something ice you said? Okay, it is colder than most ice because it's very, 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 very cold. They say, I'm not about to do it to try, if you were to stick your finger into liquid nitrogen, you should just do that, shatter your finger, just that quickly, okay? Because the temperature, if it gets incredibly cold, it can become incredibly brittle and break off really easily. Very hot, it could go to, so you see very cold, could make it break more easily. Very hot would make it go to plastic. So you see the temperature of the rock will also influence what kind of change you have, what kind of strain comes from those stresses. The speed of the stress application, okay? I push on the board and it comes back because I'm not pushing very fast. If I had a hammer and just hit it real sharply, I'd probably make a hole in the board, okay? Because that happened much more quickly, okay? So the speed of the stress application. On the other hand, a very slow stress may actually bend the rock. It may actually be elastic change if you release it in time, but if you leave that slow stress application for a long period of time, the rock may actually change its nature and be a plastic change. And then another one is the confining pressure. If this rock is underneath a whole, say 12, 15, 30 feet of soil, and you add a stress to it, you may not get much response at all. Unless maybe there was a place where the soil wasn't as thick or as heavy or something like that, and then you were applying the stress from underneath, that may bend the rock upward because the confining pressure was different here than it was here. And that may be why you have some weird shapes. So you see all these, and the interplay of all those can produce some of the observed rock structures. Now we'll see all kinds of different rock and rock structures, and we won't know what caused it, but you can even easily sort of imagine a combination of these that could cause those activities. So let's see what they show here. This is the elastic to plastic to fracture type thing. All materials, all solid materials, if you exert a stress on them, now most of the time I'm used to putting the action on the horizontal action and the axis and the reaction on the vertical. So to me it seems like the stress ought to be down here and the strain up here, because strain is a function of stress. But this wasn't a math person doing it. It was a geologist, if they cared. And maybe the graph just shows better this way. I don't know. But you see, you put a stress and the deflection occurs. Like I put a stress here, put a little stress, a little deflection. More stress, more deflection. More stress, I hit the back wall, okay? But you can put different amounts, and the stress, increasing the stress, increases the strain. Okay, that makes sense, right? Increasing stress creates more strain. Now, they have material A here. Material A will perform this elastic behavior for quite a lot of stress, a wide range of stress. Now, it happens to show here, at some point though, it's responded to the stress in a linear manner. Do a little stress, you get a little strain, a little more stress, more strain, more stress, more strain. That's linear. But after a while, you do a little more stress, and it's not responding. Now it's doing plastic deformation. Okay. This material B was responding more to the stress with more strain than A did, but you keep adding a little more and suddenly it ruptures there. In other words, it fractures. It breaks, not bouncing back. Here, all in both of the linear parts, it will come back. Once it gets to the curved part, not coming back to the original shape. Or, when it gets to rupture, definitely not coming back to the original shape. That one, after so much plastic deformation, it will rupture as well. Most things, if you keep adding stress to it, at some point it's going to break. Even a diamond. Hard to do, but you can. If you know what you're doing, you can make it break. That's where the cleavage planes come into effect. Those are the weaknesses. If you can put your little chisel right at one of those cleavage planes and hit it just right, you can break a diamond, if it's breaking along the cleavage plane. Or you could actually rupture a diamond if you hit a little too hard and not quite the right area but right where several cleavage planes came together, you could actually rupture it. I don't want to be a diamond, what do they call it? Not cutter. I guess they do call it a diamond cutter. You can have a very valuable piece of diamond, a little bit of mistake can cost you big, big bucks, because no one wants little fragments of diamond. They want a big, fancy-looking diamond. So that's stress and deformation, different ways you can. So let's look at what actually happens with rock. Okay? One response, and now, for much of the rest of the time, not all, but much of it, we're going to be talking about sedimentary rocks, almost exclusively. The reason for this is not necessarily that they respond in this way more than other rocks do, though in some sense they might. But what they is, they show evidence much easier. Because sedimentary rocks tend to be layered rocks. Because the sediment goes on top of sediment, goes on top of sediment, it gets compacted, compressed, cemented together, and that's how it forms the rock. So almost all sedimentary rocks have this layering that you can see, you can visualize. You can understand that it was a sedimentary rock. Now, if you start stressing or straining it, now you can see those sediment, those layers, weird things happening to them. So that's why we're going to focus on sedimentary rock. They originate from flat sediment deposits. Usually, the layers are usually horizontal. Most of the time, deposited by water, which makes it pretty horizontal. Okay? Then, a couple things could happen. One is called a fold. That's a bend in the layered bedrock. A bend, not a break, a bend. That would be a result of a stress producing a plastic strain. Doesn't come back to being level again, it's permanently bent. It's like what would be a good example? I think, I don't know if you can remember this or not. This may have been before your time too. Bo Jackson, y'all know who he was? An Auburn football player, Heisman Trophy winner. One of the most powerful runners probably the SEC has ever seen. They've seen a lot of powerful runners. Okay, Herschel Walker was another one. But Bo Jackson, what was unusual about Bo Jackson is, and he made it into pro football too, and was quite good in pro football as well. Okay, however, they discovered a medical abnormality that could have been disastrous had he continued playing football with all the impact. I don't remember what it was, but because of that, he decided to start playing baseball. And he was a very good baseball player. I think he played baseball at Auburn too, mostly football, but I think he played it. So he was well skilled in baseball as well. And he was a power hitter. But unfortunately, I think he struck out a bit too much, which a lot of power hitters do too. And sometimes he would get frustrated, and he would just take his bat and do that and break the bat. That was a fracture, by the way. But if you can imagine, and I don't know if he ever did this in college. Maybe, I doubt if he did. But in college, they get to use aluminum bats, right? If he had done that then, he would have bent or folded the bat rather than break it. So that's what it means, a bend or a fold. Not a fracture, but a bend. You still have the rock, but it's bent. Remember that gneiss that had all the curls and bends in them? That had produced a lot of folds. Plastic strains. Can imagine the forces, the stresses that would have caused those. Those were the strains from. Widespread horizontal stress can produce a dome or a basin. Now, I'm not absolutely sure if this is one, but have any of you ever been to Stone Mountain, Georgia? Okay. There's a lot of things I don't like about Stone Mountain, Georgia, but it's mostly things that people have done to Stone Mountain, Georgia. Some in particular I really dislike. But what forms Stone Mountain, Georgia? It is one huge chunk of granite just sitting out there in the middle of a fairly flat area, okay? But this huge, monstrous dome. More than likely, that is a result of widespread horizontal stresses from underneath, but uneven overburden on top, and it formed, I'm guessing, Stone Mountain. That would be a radical example of a dome. A basin, on the other hand, would be in the part of Georgia where I grew up, they had areas they called Grady ponds, also called wet weather ponds. There would be areas of field that were just low, and when it rained a lot, it had water standing in them. But when it dried out, you wouldn't have any water. There wasn't any fed by a stream or something like that. It was just an area like that. Well, when I took soil science at University of Georgia, I found out that those were underlain by calcium deposits, chalk deposits. And when the acid rain or other things like that came, it dissolved the chalk, and you had widespread horizontal stresses from above, not from below, and that formed these low-lying ponds or basins. Okay. Now, that is sort of a two-dimensional. Kind of a one-dimensional thing would be what they call an anticline, an arch-shaped structure. You had uneven stresses over a long area on either side with less in the middle or vice versa. That's called an anticline. Now, how I remember this, A, anticline, A, arch, an arch. That's how I remember anticline. A syncline would be the trough shape. No relation there, except they're one letter apart. But here are the A's of that. So here's an example of each of those. Which would that be? Anticline. It's an arch shape. Your younger strata, the more recently deposited stuff on top, the older underneath. Obviously, the strain is coming from below with uneven resistance on top, and it's made this anticline. Now that looks pretty extreme to me. But hang on. This would be a syncline. That would be a syncline. The younger stuff is here, even though it's really deep. The older stuff down here, obviously something's been worn away or eaten away here, and you form this one. Now this isn't exactly the same, but somewhat similar. Just up the road here, there's a road called Powder Plant Road or Powder Plant Road.
It's Powder
Plant Road. Okay? I've heard that has an awful lot of potholes somewhere, either on the road or near the road. What has happened, there's a place up there where they separate gravel from sand for the concrete mixing industry and stuff like that. And they use a lot of water. And using a lot of water, they pumped a lot out, and then you have sinkholes. Okay? If there was a line of that, this could form a syncline. You reduce the pressure underneath here, and the bottom falls out. Okay? Maybe from pumping too much water out from there or something. Here are, oops, no, okay. I think it will put up. So what are folds? Folds are bends, not breaks, bends in the layered bedrock. And again, we use sedimentary rock because we can see the layering bending. Okay? It's hard to tell in a three-dimensional igneous rock that it's been stressed or strained. Easy to see in what was once horizontal plates that are now dipped or raised or something like that. These are a result of stress produced a plastic strain. The bend is a plastic strain. If there's widespread, okay, that's the same thing we just saw. Okay, here are some actual examples. Now, what do you reckon this is? I don't know if this is Grand Canyon, but it's something very similar. Obviously, not a lot of stresses or strain here, because look at that sedimentary rock. Layers, 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 almost all horizontal. Not a lot of stresses or strains there, right? No bending, no breaking, no folding, nothing. But look at this one. Obviously some uneven stresses that created some weird strains. This would be called a maybe I should do it with my pen so people at home can see it. This would be called a, what was the S word?
Sedimentary?
No, syncline. These are sedimentary rocks. How do you know they're sedimentary rocks? Look at the layers. But look at these. That is an arch, anticline, syncline, anticline, syncline. Now it looks like there may have been a little fracturing here, or that could be just erosion. It's hard to tell. But it does look less down here, a little bit, but what? A lot up there. Something caused some permanent folding going on there. Not any breaks necessarily, but definitely folding of those sedimentary layers. Right? How about this one? This you have a lot more perspective. These are people in cars down here. Look at that. This would be a syncline, anticline. Okay? Obviously sedimentary rocks, you can see the layering, but it's no longer horizontal. Okay? Now, again, is there fracture here or is that just erosion? Hard to tell. Same thing a little bit here. But obviously at one time that was a fold. A complete, and in many places still is, a folded thing. Not a fracture, but a fold. Okay? So those are samples of that. I need to keep turning my pages so I don't get out of shape, out of place with this. Yeah, that, let me go back. This one here, that picture there, that is of the Grand Canyon. That's rock bedding on a grand scale in Grand Canyon, meaning sedimentary rock for a long, long period of time, okay? And then the next is a closer example of rock bedding can be seen in the road cut, okay? They don't mention bedding here much, I don't think. I sure don't remember that. But that is definitely a really major. The one in your book, they call them tortured rocks from originally horizontal layers that were folded by intense pressures, high temperatures over a long period of time, when deep underground. And by the way, if you remember, temperature matters here. You're not going to get temperatures high enough to cause that kind of folding anywhere near the surface. That had to have happened way underneath and been pushed up by pressures from underneath. And that's what we're talking about, building the Earth's surface. How those happen, hard to say, but they do happen. Evidence is there. Now this was, at one time, a dome, okay? And I don't see this one in this book. It was in the other edition, the previous edition, which is where the slide came from. And I'm almost certain, if my memory's right, this was Sundance Mountain, which is somewhere out west. Y'all probably don't remember the movie Butch Cassidy and the Sundance Kid. No. Okay. One of the stars in that movie was Robert Redford, and he runs, or did run, or started a film thing for independent films, small budget films, the Sundance Film Festival. I think named after the movie, but it may have been in the same location where Sundance Mountain was. I think this was Sundance Mountain. It's hard to see from this picture, but it's going up. But then you have a problem here, and that's because when the doming happened, this was a dome, when the doming was happening here, you were cracking the surface, right? Whatever was on the surface was being broken apart and stressed and broken, and then erosion came in and ate out the middle, okay? but the edges you still see the doming effect. It's just erosion has happened here. These are the oldest part of the formation down here, even though they may be one of the higher part, with the younger strata around the edges. Okay, because they were deposited later. So not always are domes like Stone Mountain, dome like that, but they had once been domed, but now eaten away. Those are examples of folding. Now we move to faulting. Now before we do that, no, we're in the right place. Okay. Faults are produced by relative movement on opposite sides of a crack. Okay? Now they're using two different words here. Okay? When a rock breaks, okay, it definitely forms a crack. If the crack has movement on either side, that's called the fault. If it doesn't have movement, it's just called the crack. Okay? Does that sort of make sense? They do mention this in the book, but they don't make a big deal about it. Okay? Okay, I'm sorry, I was saying that wrong. When they crack, if it doesn't have the relative movement, it's called a joint. Now, this is not the other kind of joint, okay? And joints are common in rocks exposed to the surface of the earth, but when they do have relative movement, that creates a fault. A fault has movement, a joint does not. So that's the two that we're talking about here. Now, in your book, Figure 19.8 shows columnar jointing. These are cracks that don't have relative movement. They're at right angles to the surface in these as basalt cools. And here's Devil's Post Pile is on the left-hand side. It's page 486. And near the San Joaquin River in California. And Devil's Tower, which we actually are going to talk about in one of our labs in Wyoming. There's a picture of Devil's Tower, and you see the cracks there. There's no relative movement. Those are joints between the basalt crystals, you might say. Huge crystals, okay? Now, so if you do have movement on either side of a crack, that's called a fault then. Okay? Now, let's talk about the pieces or the parts that make up a fault. Okay? The first, the lower side of the fault, and when I say lower, the fault is seldom vertical. Okay? It's usually at some angle. So on the bottom side, that's called the footwall. On the top side of the fault, that's called the hanging wall. Okay? So the footwall is a mass of rock below the fault. The hanging wall is a mass of rock above the fault. The fault plane is the line or the crack, the surface between the footwall and hanging wall. Now this is a very clear picture here. They show the sedimentary rock. Again, they use sedimentary rock so you can see the layering. And this is one type of sedimentary rock, another kind, another kind, another kind. And look what happened. In this one, the hanging wall slid down the footwall. Okay? Hang on to that thought. Fault, not fault. Okay, here, this is an actual picture of one. There's the fault plane there. The footwall's here, hanging wall's here. Again, the hanging wall slid down. You can tell this line used to be in line with that one. This base here used to be in line with that. This one slid down the footwall. Okay? So those are the features of a fault. There's relative motion. The lower side of the fault is the footwall. The upper side of the fault is the hanging wall. No matter which one went up or down, that's how we name it. Okay. Now the next slide gives a few more terminology. Classes of these faults. Okay? A normal fault is one in which the hanging wall moved down relative to the footwall. Somehow to me, that almost seems backwards. You would think hanging would go up, not down, but I don't know. Okay. But it slid down. So that's called a normal fault. Now, there are a couple of related features. They mention them here and never do they show up again. I had never seen these words before I taught this course. Ever, okay? And they'll show pictures of them here, okay? A graben is a block surrounded by normal faults, okay? The normal faults drop down, leaving the hanging wall raised. This would be a graben. Here's the foot wall, hanging wall went down on either side. Normal faults on either side, okay? That would be your graben. Okay? The horse is the block surrounded by normal faults. I'm sorry, I said it backwards. This is the graben. The block surrounded by the normal fault. I was thinking the faults drop down. No, it's the block surrounded by drop down. So again, foot wall, hanging wall. On either side, the foot wall drop down. The block surrounded by the normal faults, which are this way, drop down. That would be a graben. Okay? This is again a normal fault because the foot wall, hanging wall drop down on both sides. If it dropped down between two foot walls, then that forms a graben. Okay? The horse, and think of this as being hoisted up, the foot wall is here, and the two sliding hanging walls slid down on either side. So the block surrounded by the normal faults still, the hanging wall sliding down the foot wall, the block surrounded by that is uplifted. Okay, so that would be a horse. Okay, never use these things again. However, let's go back to what a normal fault is. Always the hanging wall slides down the foot wall. Slides down the foot wall. In every case, it's sliding down the foot wall. Why? A normal fault indicates you have tensional forces. These are being pulled apart. That's what created the crack, which made the fault, okay? And this hanging wall slides down the foot wall because the forces are tensional forces, pulling them apart. And that's what created the fault in the first place. Whether it's a graben, a fault, a horse, or just a normal fault. They're all normal faults caused by tensional forces. So again, the stress is a tensional force. The strain is a fault. A breaking of the thing, and then the hanging wall sliding down the foot wall because of the tensional forces. See how these tie together? Okay. All right. There are other faults. The first of these is a reverse fault. That's the reverse of a normal fault. That means the hanging wall has been forced upward relative to the foot wall. That would result from horizontal compressive stress, pushing them together, forcing the hanging wall up the foot wall. Here's a picture of it. Okay? The foot wall here, hanging wall has been forced upward. Only way that could happen if you have compressional stresses. So your stresses are compressional, your fault is your strain, and this becomes a reverse fault. Now, a thrust fault is also a reverse fault, also caused by compressional forces. However, for a reverse fault, typically it's a pretty steep angle. For a thrust fault, it's a very gradual angle, low angle fault plane. And in that case, you don't have an obvious situation like this. Generally, with something like this, As soon as that starts happening, erosion sets in, because this is a very sharp angle here. It doesn't hold together well. You don't even notice there's a fault there. You don't notice see, in all the others, there's an elevation and a depression. Here, you don't have much of that. Much, anyway, because this is a thrust fault. The reverse fault is a reverse fault, depressional drift. The faults provide information on the stresses producing the formation. Now, they mentioned plateaus before. My feeling on what a plateau is probably, let's go back here, a plateau would be something like a horse. Okay? You probably had tensional forces on either side which left the footwall elevated. The hanging wall slid down, and the footwall in between the normal faults was then appeared to be uplifted. It wasn't uplifted, the other two fell down, but it gives the impression of being uplifted. I don't know that every plateau is that, but that's at least my concept of what makes a plateau. I may be wrong on it. Okay. Any questions on the faults? Or the folds, by the way? The only difference between a reverse fault and a thrust fault, not really a difference. They're both reverse faults. It's that a thrust fault is a very shallow, low-angle fault plane, whereas a normal, fairly steep fault plane, higher angle, is going to produce the oral fault. Sorry. Goodness, by the end of the week, I'm so running out of energy. And then, too, I didn't have my salad today. I didn't have time to eat my full meal, so I'm running out of energy really rapidly here. Okay. Everybody got it? Nope, still one writing. I don't maybe know enough of the geologic features of the area. I don't know of many faults in the area. I'm sure there must be some, but a lot of our formations and things like this are much more likely to be folded than faulted. They're ancient. By the way, all our mountains here, Red Mountain, Shades Mountain, are pretty old. Okay. Now, there is an example, 19.1, that's talking about a graben, and they just throw in numbers here and do a variety of things. It has nothing to do, I mean, maybe an illustration of what the book's talking about, but really not that much to do with them. Okay? So now we're moving to 19.3, which is earthquakes. Now, we've already been talking about earthquakes, most often occurring near boundaries of plates. We certainly have earthquakes that are not anywhere near a plate boundary. Okay? Well, what is an earthquake in general? It's the quaking, shaking, or vibrating, or upheaval of the ground. Now, here they do say upheaval. It can occur. That's a little less common than just the quaking, shaking, and vibrating. It results from the sudden release of energy from stresses on the rocks. So the rocks are under these stresses, and then for some reason or another, there is a sudden release of that energy. That's what creates the shake. That could be a fracture of a rock. It could be a elastic rebound of a rock. Usually the plastic stuff is more gradual. Usually it's more fractures, I think. Okay? The vibrations are seen as seismic waves. What three types of seismic waves do we have? Three types of seismic waves. All me. We talked about them last time. We talked about them this time. Oh, how soon we forget. Three types of seismic waves. Two of them are associated with letters. Second, P waves. What does that stand for? Primary or pressure. Okay. Second, P waves. S waves. What does that stand for? Secondary or shear waves. The motion is perpendicular to the propagation. And the third was, do you remember that one? Not associated with the letter. Once it reaches the surface waves, or like water waves. So the vibrations are sensed or create the seismic waves. Most of them, not all, occur along fault planes when one side is displaced with respect to the other. So when you do have earthquakes, usually they're associated with fault planes. Those fault planes may be the actual plate boundaries, or they could just be any fault plane that occurs because of stress on the rock that it's occurring. Okay? So earthquakes are basically almost strain-like. They are the results. They accompany the strain. Let me put it that way. The quaking, the shaking, the vibrating, with some possibility of upheaval. That's not as common. They result from the stresses. So in a sense, they're kind of like a strain. They are the result of stresses. And the vibrations. But most of the time we think of the strains as being the folds, the faults, the domes, the valleys, the anticlines, the synclines, all those physical things. This is the measurable results, the motion, the shaking, the sound, that kind of stuff. All right, everybody got it? What causes these earthquakes? I thought we just said. Well, one is the elastic rebound theory. Two plates pressed tightly together. They're held together, but there's forces, there's stresses on them that's trying to get them to move. The stress builds up until the friction of the rock or the rupture strength is overcome. So the friction of the rock means you have elastic rebound, or rupture occurs and it actually breaks. The stress rock snaps suddenly into a new position. That's called elastic rebound. Okay. The one that ruptures doesn't obviously result, but the other stress rock, well, there has to be two to tangle, right? Okay. The other one rebounds suddenly, snaps into a new position, and that's called the elastic rebound theory. Okay. And here is another picture, a better picture of the San Andreas Fault. Okay. Up here is out in the Pacific Ocean. Okay. That doesn't mean that can't affect land, because if there was an earthquake out here, Eureka, California is going to feel tidal waves, that kind of stuff. Okay, but it goes right smack down through San Francisco. And in my mind, it probably is the reason San Francisco Bay is there. Probably in the past, way past, long before we were here, enough of these happened that you had the bay being formed. Okay? Here it sort of juts inland a bit, and here it's inland from Los Angeles. So when they had the earthquake here, Los Angeles felt the effects of it. It wasn't quite as major as when they had it in San Francisco, because that was right on the fault line. The fault line was inland. Now, there is some very rich farmland inland from Los Angeles and San Francisco too. So somewhere along here, you'll see a picture from a field, and it's just incredible what happened during one. I don't know which of the earthquakes it was, the San Francisco quake or the Los Angeles quake. You'll see the earth did move, transform, sliding past each other, not sliding, grinding past each other. Now here's the interesting thing to me. If you follow this line on south of here, San Andreas Fault, down into Mexico, if that is anything near accurate, what do you find south of California down into Mexico, you find the Baja Peninsula that goes a long way. I mean, fairly close to as long as the state of California, not quite. And in between that is what they call the Gulf of California, even though it's in Mexico, okay? And I can't help but think that is an extension of the San Andreas Fault. It looks perfectly to match that. I may be wrong, but just like the Red Sea is a boundary between the African plate and the, I believe it's Arabian plate, so is, I think, the Baja, or the Gulf of California could be the boundary along the San Andreas Fault between the Pacific plate and the North American plate. I don't know for sure, but if this figure is anywhere close to accurate, it looks like it's smack dab on it. Okay? It doesn't go far enough for us to tell. Okay. Now, here's the picture. I knew it was coming up sometime. I don't know which earthquake it was, either the San Francisco or the Los Angeles, but you sure can tell the fault plane here, can't you? Look at this. Those fields, this farm had been planted, and the rows were straight. There is actually, you can see the transformed boundary, the shifting between the ground on this side and the ground on that side. Now, which is which, I don't know. I don't know which is north, south, or whatever. But boy, that was a definite shift. No upheaval, no cracking and people, tractors falling in. It was just a transformed boundary. Make sense? This illustrates it just about better than anything I've seen before. Okay? Now, this figure up here, I find truly out of proportion. It's some artist's drawing and really rendered really poorly, I think. This shows the shear stresses in two different directions. Shear stresses here, one plate trying to move that way, one trying to move this way, and it shows bending a fence and bending a highway. Won't happen. Highways don't bend like that. Okay? That road would crack and crumble. But then your earthquake occurs and you actually have a fracture, and no, I've never seen any record of a full length of a highway being shifted like that. This is part of a field road. This is probably 8 to 10 inches, not 10 or 15 feet, okay? No, you don't have that kind. So that's way out. And the fences jump right back into place. No, that was sort of silly. But they were trying to make a point here, okay? I believe we're at a point that we probably should take a stop and figure to pick up from here next time. Okay? Locating and measuring earthquakes. I'm pretty sure that next time in the first 2 hours we will finish chapter 19. And in the next 2 hours we'll have our lab for 18 because we didn't have a chance for it today. And then the last 30 minutes we'll have the test for 18. If we do finish 19 that way, that means Thursday of next week we'll be in chapter 20 by then, and we'll then have the lab for 19 and then have the test on 19. So for the next couple of days, it's going to be 2-hour class, 2-hour lab, 30-minute test. At least the next 2 days we'll be doing that. Always testing by the chapter we finished before. Okay. Like today we're testing on 17 because we finished 18 today. Because we finished 17 last time. Next time will be a test on 18 because we finished that today. And then the next time, I think we'll finish 19 and have a test on 19 then on Thursday. So 3 in a row, test days, 2 in a row, lab days. But today was a long lecture day. Next 2 will be much shorter. All right. So let me turn this off.